Hyderabad on VLSI Design. Welcome everybody to this afternoon session. I request people to sit closer because there is one laser pointer, so it's easier to point to one screen if that can work. But if numbers increase, we can always spread out here. There's another room adjacent, which will be in overflow room. We'll have both of them. We have 3 speakers for this afternoon's presentation.
Look here and see the screen.
We have Biswajit Patra, Debolina Shakale, Rupesh Potineni, and the topic is disaggregation technology. Disaggregation is one of the key strategies to bring forth rapid product innovation at scale by using smart combination of chiplet ecosystem, advanced packaging, compute capacity, memory bandwidth, and unparalleled IP portfolio. Let me introduce Biswajit Patra, who's here. Biswajit Patra has been working in Intel India as a senior principal engineer, focusing on low power and high performance design and high volume SoC and advanced technology nodes for AI, ML, heterogeneous and mobile compute. Previously, he worked as principal engineer in SoC physical design at Qualcomm Bangalore. He has completed his PhD in computer science and MTech in ECE from Calcutta University and effective leadership and management from the Eli Broad College of Business, Michigan State University. During his career, he has authored more than 40 papers in national and international journals, conferences in low power SoC design. Let's give a warm welcome to Dr. Biswajit Patra. Our second speaker will be Debolina Shakale, who joined Intel in December 2019 as a principal engineer. Prior to joining Intel, she has worked in Xilinx, Freescale Semiconductors, and STM Microelectronics. She has over 20 years of experience in front-end IP, SoC design, and architecture. At Intel, she is a part of the team working on the UCIe die-to-die stack. She has filed 18 patents till date, with 15 patents already granted and rest in pipeline. She has done her BTech in electrical engineering from the Indian Institute of Technology, Bombay. Please welcome Debolina. Our third speaker is Rupesh Potineni. He's a principal engineer at Next Silicon Group at Intel. He has been at Intel for 19 plus years and played leadership roles in the convergence of several SoCs. His expertise is in floor plan tech readiness, backend methodologies, physical integration, verification, disaggregation using advanced package technologies, Fovero's EMIB, co-EMIB, Fovero's direct OSAT, development for client server IoT networking products. He holds an MS from BITS Pilani, India. Please welcome Rupesh. With that, I'll hand it over to Dr. Biswajit Patra for starting the session. Over to you, Biswajit.
Hey, good afternoon. So nice meeting you all after the lunch. I know after the lunch, probably we are a little, with the food inside. How many of you are really happy with your laptop performance? Happy? Good. How many of you are happy with your phone performance? How many of you are really happy on when you search something in Google and you get the answer? Only C. So that basically means all of us having our job. We are not happy with the current state of affairs. And that's exactly the need of the hour. So that we can keep our job running, we can keep innovating, and we can keep on doing new things. And today, we'll be discussing about how do we really do a rapid development? How do you really get a product quickly at a low cost? And how can we really build up what is need to be done? That basically is the theme of the conversation. And I'm sure many of you have worked on this technology. So feel free to interrupt us, give your thought process any point of time. It's not that everything we know under the world, and not that we are the Einstein. Just, it's a community group. We would like to have our thought process put forward, and feel free to give your thought process and enrich the community. Just as a disclaimer, what we are discussing here is not official versions of Intel. It's purely from the academic perspective. We are sharing our thought, input, how things are going on, how things should be going on. Number one. Number two, all the data, what you'll be seeing it, will be calibrated. That basically means we will not share any of Intel data here. So these are the two steps to keep in mind. Similarly, when you are bringing up your thought process, please follow the protocol, what has to be followed, so that we are all at the same tone. Just a common protocol to be followed. So with that, let me start with this. So we'll talk about the introduction, about the disaggregation technology. What is this technology all about? How can we get the benefit out of it when we are developing the SoCs? And how, in Indian context also, we can create an ecosystem so that all of us can get benefit, and India can be also becoming a silicon hub, which is today, to the next level of it. Then we'll talk about, so all of us are working on monolithic architecture to basic with, and how do you really create an architecture which is disaggregation friendly? So we can do a rapid prototype and rapid development, and we can see the silicon in hand as quick as possible. The third thing, when you are trying to do this kind of a complex SoC and structures, you need to partner with the EDA vendors. You know, develop some tool by yourself and come up with the tool flow and methodology, which is essential for the rapid development. So these are the three broad areas what we'll be covering it today, and we'll give our views and thought process and what we have experienced too, and feel free to chime in. That's the kind of a structure, just to be all in the same page. Now, if you look at it, our job is safe for next 20 years. The silicon, what you are seeing it today, is going to change a couple of 100x, if not 1,000. If you see this, probably you have seen recently, the MIT research group has done a quite significant breakthrough research where they are able to predictably make the transistors with an atom size. So that basically means you can think about how much transformations will get, and the job in VLSI and VLSI community is going to stay for a couple of years. The second interesting point, everything needs some money. And if you see near future in 2025, the amount of revenue going to come by AI business is almost $169.4 billion. And all the companies are trying to take their fair share as much they want to grab it ethically. And an interesting point, there's a lot of interesting social problem we have still not solved. And we as an engineers, we are obligated to do that job. If you see, once we all become older, our memories also start degrading. How can you really make your memories still fresh? And you see a lot of research has been already done in this area, and quite interesting stuff. You may have seen the Elon, who is able to implant a memory implant on the animal's brain and can manipulate these people. So think about the amount of positive influence you can get into the society. So in a nutshell, we have enough interesting problem to take the new technology to the new directions. And if you look at this roadmap, the IRDS who actually set up this roadmap for next couple of years, the whole companies are already trying to deploy the benefit of the chiplet-based disaggregation technology. And you see the trend. And many companies have already beat the trend. You may be asking questions, hey, AMD has already crossed, Intel has already crossed, N number of companies has crossed it. This is actually just to show that in general where academic is going forward. So in a nutshell, there is a lot of interesting tractions already happening over there. Now let's look at it, how we have started the design in a VLSI technology. In 1980s timeframe, we all try to write the schematic and then bring that into a design was the kind of state of affairs. In 1990s, started with the
all HDL language, Verilog, VHDL, and then you try to represent the design. Then 2000s was all about IP, that you develop all the companies and the huge number of companies can play an ecosystem. You develop the IPs, integrate them in a single SoC to get the complex functionalities. That was the kind of a trend in 2000. Now in 2020 plus, what are you thinking about? How can we really design a chiplets? A chiplets is basically inside the complex SoC. Individual modules are built, tested like a silicon, and then you assemble all of this together and get a functionality. So the beauty what you get out of this process is you can reuse, you can collaborate with the partner. Let's say an example, right? You are making a CPU based company and you have a lot of miscellaneous component. All you are changing primarily is the CPU. How can you really drop and replace only the SoC part, the CPU part, and make a product quickly? And that's where a lot of tractions are coming for the chiplets-based disaggregation technology. For two drivers primarily. One, how can we do quickly the stuff? The second important thing is that if you really want to design so many CPUs in a single die, 128 or maybe tomorrow 300, 400, the amount of die area you need, you can't really design that. And even if you theoretically design that, you can't get an yield out of it. Maybe out of all the CPUs, half of them will be dead. Half of them will be working because of purely the parametric variations what you have in the place. So there is a technology reasons why chiplets-based technology is coming off as well. So if you are trying to create a complex SoC and you want to build, let's say 500 cores, 600 cores in a single monolithic SoC, you can't really do that. If you do that, sorry, the question? Yes. So basically what is they are trying to do it, right? In an entire wafer, but you can't cross the wafer limit. So what you can do it, you can create a wafer. Within that, there are companies, Cerebras and all they have come across. So what they are trying to do, they have built the entire, wafer as an SoCs, but there are pros and cons in that, right? You think about this, how many cores they are actually working, you don't know. They have not shared the statistics, right? So maybe you would design 500 cores. Out of that, how many of them are actually alive in a given situation? All the design houses struggle, even with this, any node, starting from what I have seen, maybe from 90 nanometer, when the multi-CPU domain era comes into picture, whenever you try to build an SoC, you see at the beginning phase, 50% CPU itself are not working in a large stuff. And then over a period of time, you tune the parametric variations and it takes longer time to stabilize the process. So you have a good point, but there is a technology limitations and it's a parametric limitations, which takes a lot of time to come to the speed. Now, if you look at this, the chiplet based design is actually happening and over 100 designs activities are today taking in place. The multiple companies, the whole industries, the Intel, you take the AMD, they take the NVIDIA, you take any companies, all the leading design houses today are deploying or already deployed or in the process of deploying the chiplet based design to make it successful for the reason to come up and compete with the product. Maybe initially when you come up with this technology, the cost is high. That's the natural process, but it will get stabilized over a period of time. So if you see the industry, almost every company is started focusing on the chiplet based technology today, and it's not in a theoretical world today. Maybe it was there 10 years back. And this is very interesting research work is being done. This data is being used by many companies. If you see, the market will be worth about 100 billion by next 5 years, at least as a minimum, and 301 million unit is probably going to be shipped, or maybe our best case is 1,074 million in 2027. So a huge amount of market potentials going on. And Intel, we are committed to use the technology to get the best silicon for the customers as well. And if you see today, most of the companies started at the PC eras where you have seen all our mobile phone, not mobile phone, the laptop, desktop was started with this market. Then we went to the mobile and cloud area. Now people are all thinking about the intelligence edge. So that basically means we are trying to shift our gear from the classical SoCs design to a large SoC where you have a lot of intelligence built into. And when you talk about the intelligence means what? It basically means for an SoC company to develop a computing infrastructure which has a CPU, which has a GPU, which has a AI-based custom silicon, and you have the special purpose accelerator. So all of them clubbing together and giving a single solution to the market is the essential to cater the need of next generation compute. And it's already happening. It's not that if you see nowadays, not coming off.
I think the battery is dead. We will see.
Use this for that.
Is it working? Switched it on. Is it okay now? Okay. So now if you see it, sorry for the break. So if you see today, most of the companies where these disaggregation is becoming more and more important, because what we are trying to do, all the design houses, we're trying to make a XPU compute, which basically means you have a CPU, you have a GPU, and you have a AI-based special CPU you can call about. And when you are trying to do this multiple stuff, and also you look at this, right? The cloud and the edge also getting mixed up. Many times you want a faster response. So you need to keep the infrastructure close by. Sometimes you can wait for the long time for the cloud response to come. That's why I ask the questions, are you happy with your Google search stuff? Most of us probably not. Now, if you try to get this, you need to build the infrastructure such a way it can take it to the next generation. So you need the complex XPU, you need the high bandwidth memories, and as much as possible inside the SoC. Now, if you want to get that, one of the way of doing it in a large PCB board, you try to assemble all of this. But then when you try to communicate from the one SoC to the other SoC, it needs the speed goes down. So what is the solution? The solution is to see if I can assemble all of this inside the package, ideally inside the one single SoC, single structured die. But if not possible, at least assemble inside the package and connect them through the high-speed interface. Keep the memories also inside them as much as you can. So you can create a computing infrastructure. That's why disaggregation strategy, if you think about, it was there at the earlier. It was happening in the PCB world. Now, if you think about that, it's shifting inside the package. And it's happening, maybe the next generations will go, everything will be happening inside the die itself. So that's the generation gap we are talking about, or the changes is happening. And in this front, if you look at it, 2019, the first time, Intel shows that the 3D IC, where basically the multiple SoC you can stack on one top of each other. We announced in 2019 in CES, the first two active die sandwich on one top of each other and make an SoC. And that become the industry's one of the budge SoCs to make a technology SoC. So I'm not talking about the commercial part of it. That's a different story. But first technology SoCs, which is basically use the technology and show the world it is possible. And after that, a lot of product has been already in the pipe or already being done. What is being already announced, I can tell it to you. The Pontific, which is being already announced by our CEO last year. That is a 47 chiplets. So we have designed and shown the industries that yes, it is possible. You can get the speed, and that is going to be used as one of the supercomputer tomorrow. So the technology, what you need, and you can build in-house, you can partner with somebody, that's a different question. So the entire design community need to have the technology and the tool and infrastructure to get the best out of it. Now, if you see, let's spend a few minutes about this technology. What is this technology all about? If you see here, classical package you have seen, inside the package you keep one SoC, one die typically. And then from the die you take the, from the C4 or the package bump, you take the connections out and go to the external void. That's the typical standard SoCs. We have seen it for ages. What is different here you think about? So you have a one die. This was a 20 nanometer die. On top of this, there is a 10 nanometer die. The two die, the metal facing each other through the micro bump. You see the tiny small pieces. These are all micro bump. They're connected to each other by micro bump. And these two SoCs are sitting. And if you look it out, they are on different technology node. So one is a 20 nanometer, another one is a 10 nanometer. Why is that? Because for a CPU, you need the lower technology node. For the other miscellaneous activity, you don't need that. So you can actually do the cost optimizations, not just the cost. The moment you go to the advanced technology node, you pay the extra leakage. The higher technology node, your leakage is lower. So if you are trying to create a product where you need a lower leakage, you can do mix and match. So it also gives you the benefit and flexibility to choose the node based on the functionality what you are designing for, not necessarily just change your gear to the advanced technology node for everything. That's the another beauty what you get it. Now, if you see over here, the way I'm just trying to spend some time on this diagram, and this is a public, you can actually see, if you Google it, you'll be finding it out. So these two technology node mixed together through the microbump connectivity between them. And then think about the challenges what you see with this as a design community. From the package, all the signal and the power goes through the base die or the ground floor die through the TSV. These are the silicon vias. Through that you make the connections. It goes through this, come to the base die again. It also goes to the compute die. So that basically means the classical way of thinking, the signal and the power, how it goes, it changes. Now, you can do the visual inspection for 5, 10, 20, 30, 50 pins. How do you really do that kind of a validations for hundreds of pins? How do you really make sure that the power, every transistor sitting on the base die or the ground floor, and also in the first floor or in the top floor, get the required power supply within the tolerance limit of, let's say, 5 millivolt or 10 millivolt, whatever limit you keep in this your design house. That's the unique challenges which you have not seen in the earlier. Now think about the regular case when you have a single die. Your heat, the way it goes out from the transistor to the outside world, the system changes. You can have a workload or a content running both at the compute die as well as in the base die. So your heat flow mechanism actually changes. How do you really create the system so that you know the performance is predictable? You are not designing something today and tomorrow you see a surprises. So this put a new set of challenges which was not there earlier. How do you really know that? Let's say today somebody is doing a floor plan. How do you know that these microbumps are planned such a way they exactly overlap on top of each other? It's not just a manufacturing guy's problem. It's also a problem for as a design implementation community to ask, how do we align them? Because this kind of problem was not there earlier when we used to design the monolithic SoC. This is the new set of challenges. And what benefit you get? You get a benefit in terms of the yield. You can divide and conquer. The smaller die gives you a better yield by nature. So instead of making the whole functionality in a single die, once you slice by, let's say, 50-50%, you have improved your yield number fundamentally. It also comes with a lower cost because you can choose a higher node and the lower node in mix. you can get a best power. Well, how? You can operate the different voltage point in the different node, and you can tune the leakage or a dynamic and static based on what you need. And you can get a smaller size. It's like a Hyderabad building. If you come from here to where everything is a tall. If you want to create the same kind of facility in a one-floored building, you need probably much more land, 10x more land. So you get a smaller form factor and faster time to market. Why? If this particular chiplets is already available to me, what I can do, I can quickly design one die and ship the product. I don't need to do this one. So this is the kind of a thinking what you need. So in this technology, we are committed to develop this technology. I'm sure many other players as well. Now let's take this picture a little more electrically. Not coming up.
There is latency.
Good question. So microbump typically is a very small patch of 9 micron, 10 micron, 20 micron radius copper. The resistance of that is couple of milliohm. Okay. So now when you draw a metal typical from one transistor driving to the other transistor, the resistance is of the order of kilo ohm. And the microbump is only 5 to 6 milliohm in that range. So it's very insignificant to impact any of your performance. And typically the micro ballpark number I'm talking about, not any technology number. And similarly, if you look at the microbump, their inductance is of the order of 10 to 20 pico Henry. And coupling components are very less. So that way, it doesn't become a bottleneck for you for any of the performance, electrical performance parameter. The interference is also something, if you think about this, between the two copper line today, what you are drawing, let's say, what is the pitch? 2 to 5 micron. AP layer, topmost layer if you're talking about. Some of you are here, the layout folks, you know. 2 to 5 micron. I am not specific to any technology node. Here, we are talking about 25 to 50 micron, the gap. So you don't see that kind of a problem for the digital circuitry. For the analog circuitries, you have to be a little careful. You have to do some 3D simulator. So if you have a complex signaling, which goes for a couple of Gbps, those few specific lanes, also based on our studies, we have seen not much interference, but you have to do the study based on your use cases and then take the call. But pure digital, not a problem. Yes, it's a problem, an opportunity for all of us to solve it. So if you see it, good questions you asked, I think I have some foil there to cover it. Now let's think about just the same problem. I'm trying to show the problem to you so that at least when you design, you know what to be taken care. Idea here is not to give a solution. Idea is to think about potential options that we can use to solve the problem. So if you think about the good questions you raised about the power delivery, you see the same stuff. I just put it in a little magnifying glass. It comes from the base die. This is your typically the package side pin or a package bomb, whatever you call package ball. It goes to the package, it goes through the base die, then it goes to the compute die to the micro bomb. So this extra electrical path, what you have it from here to here, is going to cost the extra drop, voltage drop. Not just that. When monolithic die, let's say you take a 100 micron square area. Let's say bump pitch, you take about 100 micron. So you can keep your 4 bumps that only supporting the one die's power supply need. Now, when I have a first floor and ground floor, both the same number of bumps need to support both the need of the ground floor and the first floor. So physical real estate actually has reduced because the BUM technology today, the package side BUM technology, the transformation is not that fast. Today, base technology in the market, probably about 90, 100 micron kind of thing you can get at the best. The little bit cheaper technology is 200, 250 kind of stuff. So that's the unique challenges it forces. But is it not a solvable problem? Yes, it is a solvable problem. So when you create a more number of parallel paths, you take extra metal layers and start to solve that problem. So these are the things you have to articulate when you plan your design. Otherwise, you will see a backfire down the line. So if you think about the silicon package and the board, electrically, once you articulate the extra delta between monolithic to the 3D IC, or you call about Foveros, different company has a different code name. So basically, primarily the stacking technology, I'm calling it a generic terms. Intel may be using something else, NVIDIA using something else, or maybe AMD using something else. You may be using something else in your startup. So it's all varies. Bottom line is that this electrical problems you have to solve. The another interesting problem comes into the picture is that the heat flow actually has changed. So thermal and PDN need to be think differently compared to how you think in a monolithic SoCs. The another critical factor is to think about when you are trying to create this kind of a construct, the Foveros kind of a construct, the power thermal definitely is obvious challenges it comes into a picture. We can foresee the testability. Earlier, when you have some debug stuff to be looked at it, we have so many advanced techniques to do the fieving, fieve layer by layer, go and check where the transistor pinpoints is there. Now it has become more complex. So a lot of innovations is needed for the testabilities. How do you test your silicon? If you find any issues, if your customers is reporting some issues and it's related to the base die or the ground die, first you identify where this functionality is located. It all becomes a little complex. And that's why the engineering challenges and opportunity for all of us to solve this. Now, the monolithic versus disaggregated, and there is no free lunch. In technology world or a business world or nowhere you get a free lunch. There is some cost attached to everything. Now, if you see this monolithic versus disaggregated, monolithic by nature, if you can integrate everything in a single SoC in a same floor, you get the best performance most of the cases. So when you try to disaggregate it, you do some compromise, a little bit. Yes. Now that how much compromise you will do, that's you as a designer, as an architect to decide and take the call. The flexibilities is very limited when you do a single SoCs. You have to build this entire SoC at once. You have to do the yield study for the entire SoC will mature at the same point of time. You can't add a simple function. Let's say tomorrow I have a CPU and I want to add a couple of new instruction set pertaining to a particular workload. Because today, what are the challenges? It's not that we have a very good architect by every company. The challenge is that when they design the hardware, what instruction set they will add? Because the workloads are changing dynamically. Earlier, you think about, let's say financial market, the option trading. Earlier, people are not thinking that the compute I will use to get a gain there. Now, if you see and read the literature, a lot of supercomputer innovations are driven by them. They are saying that, okay, if you can give me ideally a couple of nanosecond order latency and a computing platform, a business house can make a lot of money by simply doing the currency trading into multiple currency and loop it. So computing need and dimension is rapidly changing. That's the essence. It becomes very difficult as a architect, CPU architect, what instructions that you will add. And if you want to add a couple of them, you have to again make a new SoC. Now, if you use the disaggregation technology, let's say I only want to change this particular portion, I'll just change that. The remaining portions I can use it. That's the beauty what you get. So that's why I'm calling about flexibility limited versus, very limited kind of thing. The innovation space is faster because you can rapidly change stuff what you want to do. And it's definitely the scalability is much higher in the disaggregation technology. And this foils actually we from the Intel also shared in this last year hot chips. So I've just reused from there thanks to my friend Wilfred. And if you see it here, the monolithic versus disaggregated, can we get the monolithic performance with the disaggregated architecture benefit? That's the high level engineering challenges all of us should work towards. That basically means I can design the disaggregated technology with the lowest latency, with very high performance, faster convergence, and higher speed. That's the kind of a game-changing phenomenon, what innovations we need. And every company is trying to do that. Now, future of computing, I was talking about just a few minutes back. The computing space and the landscape is changing very rapidly. Earlier, the CPU and the GPU is primarily used to do what? Let's say you're using the phone. Earlier days, the CPU, so small CPU core was used to be used, was usually used to help to make some call, the monitoring and stuff. Now you see the situations have been changed. Inside each of your phone having a kind of a desktop, what we used to use probably 10 years back. So what are the challenges coming right now for each of the companies need to spend a huge amount of money for the thermal and the performance envelope. How do we really create a system which is within these particular thermal and power? So many companies there need to pay more energy bill than consume a silicon today. So you will be getting an order saying that you be within that envelope. I know you can give my higher performance. So it's now the question coming performance per dollar, not coming the question about a pure performance. So how do you really create? Why I'm coming to this point, using the Foveros technology, you can quickly use the multiple SKU for the same silicon. So you change couple of components, make a quick silicon and cater the different market need instead of making a single silicon for everybody. So the custom silicons makings become much more easier using the Foveros technology or a 3D IC technology, or you call it disaggregation technology than what you used to do it earlier. That's the essence. And that CPU, GPU, and XPU, they're all merging it together in a single structure. Now, what we are talking so far, I think it has a 4 part of it. One is the basic technology, I would say. The basic technology is what? How do you really create these microbomb, which is the new concept? How do you really create the silicon vias, which is basically throw the die, you make the connections, the punch through is basically a copper pillar, a strong copper pillar. How do you really create those technology? It's not easy because remember, when you are trying to make a drill through a silicon, such a long copper, there is a reliability issues. You have to make certain diameter of that piece. Not just that, when you try to make such a long copper pillar, in the process wise, there are challenges. Because when you try to create an active, even the digital circuitry to the neighbor, there could be a potential asymmetry, potential problem. How do you create a separate clearance zone over there? So those are the technology areas where we need to focus on. So when you talk about the bringing up the new technology, it basically means how seamlessly close to 100% yield you can produce in terms of the microbomb. Think about this. Even today, with this large C4 bomb, which is typically about 80 to 100 micron kind of a diameter, still you see the yield problem. If you try to make a big, let's say 500 millimeter square kind of a die package. Now, when you try to make the same smaller structure, how do you predictably build that? So that's the technology innovations needed, and every company is spending some time and energy to make it predictable fine print for them. The TSV technology, how do you make it? And best microbomb technology is what? There is no microbomb. That basically means make the 2 die put on top of each other, they get connected. Maybe keep some marker, couple of 2-micron marker. And that technology also is coming up, wafer on wafer, where basically all the design houses that wanted to make a wafer, sandwich on top of each other, and just make the connection. You can reduce the pitch also, just like a single extension of a die. So those are the technology stuff need to be done. Let's say technology you develop, that itself is not enough. The architecture, so typically what happened, right? All of this design has started maybe 20 years back. All the AI algorithms, what you are seeing it today, the published work of most of them is long back. Thinking of what? They've all thought about a single monolithic structure as a structure. How do you really make this disaggregation friendly architecture? My friend Devolina is going to talk about some of this in her session. The third important portion is the design methodologies. We can talk about all of this. Technology is available. Now, technology need to be consumed in terms of the PDK for development of the SoC. We need to have some EDA tools where we can visualize this structure. Think about this. If I am today making a SoC with a 47 chiplets, I should be having a structure to see all the 47 SoCs. They're really connected to each other. So seamlessly, and tomorrow these systems will be maybe over 100 chiplets, 200 chiplets. So a lot of work for the EDA companies to develop the design methodology. I have an RTL which is a single structure today. How can I really create a seamless partitions? Some part can be designed here, some part can be going here. And if there is a functionality, orthogonality, can we really push something to the lower technology node? How can I design the clock where the frequency of the operation I design what it must be needed, not overclocking, because overclocking also costs extra. So those are the design methodology questions need to be answered. And a lot of areas work where there is, I would say 10-20% work is being done by the design houses and then EDA people. We are also a lot of work to be done by Intel. I'm sure by most of the companies to make this to a true transformations. How can you make this design with a lesser number of resources? Today, a lot of huge gang of people are needed to do this job. And then the last but not the least is a multi-physics validations. This is the logical domain you checked it. How do you really know the power delivery problem? What my friends raised here. How do you really solve the EST? So typically, one of the way of doing, okay, each of the tiles, I will make the EST compliance and I will make this. But then you are paying a almost 5x, 10x extra tax. How can you make and visualize an ESD simulator where the multiple chiplets you can take it together? So a multi-physics, power delivery, thermal, mechanical, performance, all of this together clubbing a single suit you can test. Today, if you see, ask any design houses, they have a recipe. They have a recipe in 10 different pockets. They work together, they run a mammoth stuff to get this all solved. How do you really take this out to the next level? Now, this is the single foil. Yeah, we'll calculate it, but we'll cover up with that. Now, if you look at the tool set, this is purposefully the same picture. I just put it in a different way. What is you need? You need a technology. Just when you want to make things into reality. Technology, what things you not need? I just talked about, right? The Fourier spec RC model. You need the resistance and capacitance model for the microbump, for the TSVs. What you just asked that questions, right? How do you really know that how much performance I'll get? You need the quantification. So that has to come from the PDK in terms of the standard offering, whether you are, you use the Intel IFS service or you use the, the TSMC service or any company service. You need to ask those technology questions to them. And you need to also ask them that, hey, if there is think about this, when you try to sandwich this 2 die, by default, the microbump pitch is a common. That has to be common, right? So both the process what you choose, they must be supporting this common bumpage. So that's why it is important to have this, the aligned with what you want to take it out. Maybe tomorrow there will be a consortium where it will be standardized, but today it is not fully. So the new TSV, the TSV also different companies use a different dimension, different stuff. How do you really get that information in terms of a technology bundle where you don't need to spend your time to find out how the TSV's construction and other reliability, it comes to you rather as a packet to you. That's the technology. The second is the die in the package. How do you really make sure you design your die earlier? Maybe you use an API, any auto placement and route tool to design your your all C4 and all. Now that need an enhancement. And once you design it, how do you validate that? That's a die and package level, there is a change needed. Similarly, when you design a front end, earlier TSV was not in the picture in the front end side at all. So those feed through connections, how do you model? How do you run the formal? When you have the same function scattered across the 5 dies, how do you run the formal? So you need to think about how do you run the front end, similarly the construction. So when you design the power grid, how do you design the power grid with articulating all the needs together? At the same time, you don't overly design, because if you give everything for the power stuff, how do you allocate the resources for signal? Similarly, you have to look about the, sign off, which is basically the multi-die, the regular sign off what you run for timing, power, performance and stuff. So you need to think about all of this to come to this stage. And then last not but the least is the power delivery, which is a unique challenges. Now, if you see some of the solutions, what you can do it is do the early analysis, create a model for each of the die, test it concurrently at the very high level and check that it caters both the need for both the die that's needed. Earlier, you in a monolithic die, okay, I will allocate some 15 to 18% metal. I know my design will converge. Here is not the case. You have to think about and plan it up front. Similarly, when you are working with the EDA companies, get an early engagement. This is a structure I'm going to build. Show me in your tool what extra add-ins needed so that I can visualize the entire stack. Otherwise, you don't know what you're making. Some cases with small mistakes may cost you a dead on arrival chips. And clearly define the sign-off strategies. How do you sign off each of the items? Starting from the validation, the front-end validation, to the back-end, which is basically your LVS, your LEC checks, all the kind of checks what you do. You have that model. Now, this is the one of the area when we were trying to design an SoC, this is again a representation picture. We found out some of the spot which was we were not able to find out by doing a visual inspection after spending even a lot of engineering bandwidth. So you need to have a 3D IC based power delivery solution from any of the company. You can take it. You can take it from Inancies or the other competition solutions also available. So you can use any of them and try to find out where are the weak spot. Otherwise, you may lose a huge performance. Because nowadays for CPU, GPU class of it, millivolt per megahertz is quite significant. Tell you the thermal, maybe many cases, you see this is the one of our, representative design, not for anything else. You look at the thermal new spot comes out and there is a variations to see. So it's good to do the thermal analysis upfront to articulate how the heats are going on, and that you can find out some unique solutions over there. That how do I really improve the metal density as an example and use that one as a factor to heat to goes out. So it's a lot of opportunity. I'm sure here we have a lot of academics plus the communities. We have a huge amount of opportunities to create a chipless ecosystem. The testability debug is still a big challenges. The yield, the combined yield together, how do you solve that problem and make it cost effective is a big challenges. The next generation architecture. Can you really get the architectural benefit? Coming over here using the technology is the huge challenges, and the multi-physics simulation environment. How do I really simulate thermal, EM, power delivery together in a same multi-physics engine suite? Today, we don't have a solution. We have pointed solutions by many EDA companies. Huge opportunities and challenges in front of us to go to the next level. Now let's wait for Devolina. Maybe we'll take the all question at the end. Much more question. Devolina will cover the architecture part of it and see us tons of expertise over there. So let's listen from Devolina.
Hello. Hello everybody, I'm Devolina, and I'll be talking about the architecture perspective. Basically, I mean, Biswajit covered a lot of ground on the technology. He also covered a lot of pros and cons. I'm going to give a perspective from the architecture. What are the things that are needed when you're trying to design your disaggregated solution. So let's get started. This is more or less the agenda that I'm planning to cover. First of all, the why of disaggregation, and I know Biswajit covered some of it. I'm going to quickly touch upon what are the pros and cons. And I also want to bring upon a point, which is what are the conditions where you desperately or definitely do not want to go for disaggregation. So what are the use cases or what are the solutions where you believe that, it's not viable to go for disaggregations? I'll be touching upon that. I'll also be covering the how of disaggregation, which is where I'll spend most of the time. What are the functionality that you typically want to disaggregate? Where do you make the cut lines? What are the considerations for cut lines? So those are the things that we'll touch upon. And what are the things that you need to consider when you are disaggregating? So what are the flows that you need to take into account? What are the other considerations that we need to think through when we are thinking about disaggregation? And finally, I'll touch upon UCIe, which is a new protocol which was released last year. I'll touch upon a little bit about that. So let's get started. Okay. So the why of disaggregation, and I'm going to go a little fast on this because I know that Biswajit covered a lot of this in his talk earlier. He talked about the easy mix and match of technologies, and I have a quick example over here. Like we all know, right? The latest technology is going to be very much expensive, a lot more expensive than the N-1 technology. Now the question is that you have some part of your logic, which is, let's say, your key part, your let's say your core or your graphics cores that you want to run at the highest frequency, where you want to get the maximum performance, and obviously you want to put that in your end technology or the greatest and latest technology. But the rest of the part, the SoC part or some of the IOs, maybe it doesn't make sense to put all of that in the NF technology so as to pay for the maximum, the best, the latest generation technology. So you might want to partition your entire solution in a way that you can put the not so key part in your N-1 technology node, while let's say the cores or the graphics you want to put in the NF or the latest and the greatest generation. The other thing that, we get a very easy way of doing it is that we get a very easy mix and match of technologies. You have your internal technology node and you have a third party technology node. You can mix and match. You can find out what is the best price point that works for your solution, your product, and then disaggregate your solution and have a mix and match of these dialects that can sit together and work. Again, I think Biswajit talked about it. It allows you to get a much easier and better products QA. You don't want to be having products with the biggest number of cores because that will not be catering to a whole range of market segments. So you can get your base die. Let's say the base die can be a particular set of solutions or logic which is common across your entire market segment. While let's say the key part, the cores, you can have multiple varieties of those cores and you can mix and match these things so as to create a whole variety of SKUs that can cater to a larger market segment. You can have CPU dies with 8 cores and 16 cores and 32 cores and then pair them with the same base die so as to get a much better product skewing. I think Biswajit also talked about the faster pace of innovation and refresh. For example, in this case, you have an accelerator die, and we all know that the AI technology keeps on changing. Every 6 months or so, we have some new algorithms, some new workloads like Biswajit talked about. So it's much easier for you to have that particular part of the logic in a dielet that can be swapped for a more recent version of the dielet much quicker in a much seamless way than to come up with the entire SoC and kind of replace the entire SoC all. So that allows you a much faster rate or pace of innovation and refresh. We also talked about yields, right? And a quick diagram over here which shows that the bigger your dies become, the percentage of yield that you get out of it becomes smaller and smaller, simply because one error can impact a much larger die area than it would in a much smaller kind of a die area solution. So as a result of all of these things, we see that we get a lot better flexibility in terms of cost, total power, time to market, die reuse. So all of these things are kind of work in your favor when you can use the disaggregation technology to your, to your advantage. So these are the kind of pros. However, let's also quickly touch upon what are the cons of the disaggregation technology. And I think somebody talked about the latency. So yes, you do need to account for a higher amount of latency that comes in from, let's say, your core to your memory, assuming your memory is on a different dialect. So all of these things, I mean, basically, if it was in a single monolithic die, there was an X amount of latency. But now if you disaggregated them and your core is on a separate dialect, your memory is connected to a separate dialect, you have to pay for this additional latency that you get when you are traveling from one dialect to another. All of these things need to be taken into account. Higher complexity, obviously, like you had all your functionality, all your logic in a single monolithic solution. And now you need to have a way to partition it. You need to think through what logic goes where, what logic has to be, bundled with what. So all of these things need to be planned through, and that brings in a lot more higher complexity. We'll see some other aspects of this as we go further in our slides. All the flows, yes. So not just the functionality, but the global flows also need to be partitioned across these multiple dialects. So again, something that needs to be given a lot of consideration when you think about disaggregating your solution.
That last part?
Yeah, actually, I have more slides later. We'll go through them in a lot more detail. This is just like a overview, kind of what are the pros and cons. Area overheads, again, something that's kind of becomes obvious when you start looking at the next level of zoom in details. When you have all of these dialects, they are talking to each other through something, some technology, right? There has to be a PHY, there has to be a die-to-die stack that's kind of pushing all the communication signals from one die to the other. So which means that you'll end up adding a lot more of these die-to-die PHYs and the die-to-die stacks in your overall solution, which was not there when you had the entire solution in a monolithic die. So which means that overall, you will have to pay for an area penalty as well when you go for a disaggregated solution. Again, probably when you have to finally weigh the pros and cons and then figure out for your solution, for your product, for your market segment, what makes best sense. But I'm just kind of giving you an idea that these are also additional things that that will kind of be that come on the con side that you need to take into account.
So you probably have to normalize it with respect to
Yeah.
ISO.
Absolutely, absolutely. What I'm saying is that it is not that the moment you partition your functionality, it's going to be a little bit more than that. It's not like, okay, 4x, it's 4x plus y, where y is the additional area that you need to pay for. Earlier, you had your entire functionality, which was probably 4x, which was a monolithic die. But now when you partition them, you'll have to add this additional PHYs, the additional die-to-die stack area that needs to be accounted for in your overall area. Right. Yeah. Interoperability challenges as well. So in an ideal world, we think about a world where, let's say, I have one dialect from one company, another dialect from another company, and if they're talking the same language, let's say, I should be able to interoperate across them. But again, that's like in an ideal world, and obviously we need to make sure that both these dialects are talking in the same language. And forget about dialects from different companies, even dialects from the same company from the previous generation and the next generation. Even making them talk itself is a big deal in itself, because the flows might have changed between the n-1 and n. There might be a lot more new changes that might have happened in the functionality, how it's being split. So all of those things come up as interoperability challenges that we need to think through when we are designing our solution in a disaggregated manner. Thermal challenges, I think Biswajit talked about that. We have to plan for, if we are stacking up all of these dies one on top of each other, how's my thermal solution going to look like, and that in itself is a complex subject. So these are the cons. So we only look at the pros of it, but let's say we also need to kind of weigh in the pros and cons to understand what works best for our solution, our product. I have a slide over here which says that when it does not really make any sense to do disaggregation. So obviously the pros do look a lot better than the cons, and that's why the entire industry is moving towards disaggregation. But there are certain cases, certain niche areas where we believe that it's probably not a good idea to go for disaggregation, especially when you're looking at low cost solutions, because the amount of complexity that you need to deal with when Mr. talked about the tools and flows, the methodologies, the overall global solution, the partitioning, the die-to-die stack. There are so many complex things that need to be taken into account that if you have a, let's say, a low-cost solution, you're targeting a very, very cost-sensitive market where you will not have the additional margins to take care of all of these challenges or, these packaging solutions. It's probably, better to go with a monolithic kind of solution. The other thing is performance being a key differentiator, right? So we talked about the key technology, for example, let's say the core or the graphics we want to put in the nth or the latest and greatest technology. Let's say your product or your solution is not really the one that's going to cater to the high-end market, the highest performance market. Probably you might want to consider and you might want to weigh in the pros and cons and decide whether it makes sense to have a disaggregated solution or a monolithic solution works best for you. Similarly, smaller die sizes, if your die size anyway is smaller, which does not really have to pay the challenges that we see from the higher die sizes, and the reason why one of the pros was that, okay, when you go for smaller die sizes, you can get better yields. If that's not really a challenge that is there in your solution because you already have a low die area solution, then probably if all of these things are kind of a tick mark for your product or your solution, then you might want to think about whether, disaggregating the solution or product makes sense for you. So, just kind of a catch over there. Okay, with that, we move to let's say the key of this presentation, where we're going to talk about the how of disaggregation. So first, I want to talk about the cut lines. Like, what are the logic areas? What are the things that usually people want to remove in a separate dielet, in a separate chiplet? What are those key things? The graphics and CPU cores are, I think on the top of the list. We've seen multiple examples of that in the industry as well. Here I have an example of Intel's Meteor Lake, where both the graphics and the CPU die, they are in separate dielets. And like we said, right, I mean, we want that to be in the greatest and the latest technology node. So obviously your cores, and that's the key area. That's your key performance differentiating part of your solution. So you want to disaggregate them in the latest and greatest technology node. And again, you don't want to put everything over there because that, adds up to your cost. It also gives you the ability to scale independently. We saw the examples earlier where we said that, okay, whether you want to have 8 CPU cores, 16 CPU cores, and whatnot. So all of those combinations are much easier when you have these things disaggregated in a separate dielet.
In terms of RTL, it's the same as building separate.
So usually the core IPs, you do get core IPs, right? I mean, you have a separate core IP. Now, in your dielet, you need to decide how many core IPs you need to put together to make a CPU dielet, right?
Yeah, I mean, if we divide the whole system into some teams, building each of their own chiplets. So is it like previously they were building separate IPs and they were integrating that? Is it same like that, their chiplets as well?
Yeah, similar, right?
RTL.
Yeah, exactly. It's like a chiplet is nothing but a smaller SoC, you can say, right? In some ways, it's like a smaller SoC. It's just like, but the other additional thing is that it's talking to yet another SoC. Instead of just talking on IOs to external things, it's also talking to another SoC. So there are certain flows, we'll talk about that needs to kind of pair up, and that has to be aligned for both of them to be talking the same language. But in a way, you can think like it's like a smaller SoC developer. So if you were developing, let's say, 8-core dielet, and there's another team that's developing a 16-core dielet, both of them can be developed in parallel, and then you can create a product out of a base die plus 8-core, base die plus 16-core. That gives you two different product flavors for different market segments, right?
Does this help in providing this high-speed service? Like I have a very high-speed ADC and I'm like a service. So instead of that, can you put the digital core and then analog? Can I directly connect without service?
That is, you still need, even for the die-to-die, obviously when you're talking across these two dielets, you will require a high-speed service that's going to be there.
You cannot do directly the parallel lines in PSUs.
At least I've got, I mean, very high frequency TSVs, I don't know, maybe Biswajit can talk about that.
TSVs will probably not meet it. Again, case by case, we can discuss offline. But if you think about a TSV is nothing but around 20 milliohm to 40 milliohm resistance, about 20 to 30 picohenry of inductance, and a coupling is almost negligible. So with that kind of this R and L is going to impact your performance. With that, you need to do a what if to see what it means to you. So I don't know give a pointed answer, but generically, if you take that RL circuitry and put that into your equation and see if the protocol is remaining intact, which may be yes, but you need to put that in a simulation environment, both functionality test and the electrical test. If both of the answer comes as a yes, then you can apply. Does it answer your question?
I mean, does it reduce the performance requirement of ZS?
It's some order, but that order is what it need to do these two tests to get the answer.
So, for example, one of the technologies that I'm going to talk about today is the UCI, the Universal Chiplet Interconnect Express. So that does even, I mean, that which is a, let's say, an open source specification that has been donated by Intel last year. Even that has a file. It's a high frequency and very high bandwidth file, which requires a service. So it's hard to get around that problem. You have two chips communicating with each other at a very, very high bandwidth, high frequency. You would need some kind of a, and it has to be reliable also, right? I mean, you need to make sure of a lot more things. We'll talk about that. Like, it's not just about signal passing through. What if you miss something, right? What about retries? What about CRCs? All of those packet processing, all of those things come into the picture then.
So when we say chiplets, we are always talking about the 3D stacking or on the silicon interface.
Yeah, that's also. Yeah, I think City talked about
it. Also is another way of doing it. It's a 2.5D we call.
Yeah.
And if you are doing on top of each other, it's a 3D. It's a just naming stuff, but yeah, many companies go to 2.5D and 3D. But 2.5D is a connectivity through a silicon interposer.
I think Pontevico example that he gave about 47 chiplets. They had both, 2.3D versus 3D as well. 2.5D and 3D. Yeah. So so the final point over here is that when you talk about GPU cores, why does it make sense to have a GPU core as one of the dielects is because if you had a discrete graphics card, that's going to take a lot more power. The overall power envelope of the solution becomes a lot more than if it was inside within a package. So again, these considerations make graphics and CPU cores one of the most, usual suspects for having a disaggregated solution in a disaggregated dielet, let's say. The other choice is the IOs, and this is on the other side of the spectrum, let's say. Whenever you move to a new technology, all the IO files will have to be done all over again. So that's like a huge cost. It increases the time to market. So which means that it makes a lot more sense to keep the IOs in the previous generation, the N-1 generation, let's say. Plus, now here I have and these are not usually performance critical. It is probably okay for your solution to not go to PCIe Gen 6, maybe PCIe Gen 5 also works, let's say. So, these things make the IOs also a disaggregation good candidate for disaggregation. Here I have a very good examples of Intel's Agilex. And as you can see, these 5 different dielet options are there, each of them providing different amount of bandwidth or throughput, 32 gig, 116 gig, 16, 28, 58 gig. So which means that having all of these different dielet allows you to have a lot more SKUs, a lot more combinations which are possible for different market segments. So depending on your customers' needs, your customers' market segments, or what is the kind of IO bandwidth they have, their needs, you can actually play around with these chiplets and dielets and create custom solutions for your customers. So again, another very good example of having a disaggregation solution. I think it is 2.5D, right, Biswajit? Agilex is 2.5D. Yeah. Here is an example from AMD Zen 3, and another very good candidate for disaggregation are the caches. It Now, normally when we think of caches, we are thinking about some range of megabytes, but here in this AMD's Zen 3, the V cache provides you a whopping 64 megabytes of SRAM cache. Having this in a single dialect, in a monolithic dialect, would probably not be feasible for many different reasons. So this is another very good way where you can allow much larger caches to be sitting closer to the cores. When I say closer, again, it's in a different dialect, but still it might be sitting just beneath the core. That's a possibility. So if you wanted to have a much larger cache, this could be a very good way of disaggregating them. Usually we have seen that the SRAMs and the memories have an affinity to a particular technology where they do best as opposed to the rest of the logic. So you might want to choose the technology that works best for your SRAM and then disaggregate that part of the logic and have the normal core logic sitting on a separate dialect. So another very good example of where disaggregation makes a lot of sense. Okay, I don't want to talk about whether it's a fancy term or not. Yes, that's what they're doing. They are actually placing the cache on a separate dialect and the cores are placed on a separate dialect. So, yeah.
Say you are on the same diversity.
Yes, yes. I do have that slide. Just hold on for a second. Yeah. And in fact, what we're seeing, the trend wise is that the latencies overall, that gap is kind of reducing. Initially it sounded like a much bigger gap when you move from one dialect to another dialect, let's say for a memory access or something, but that gap is now reducing. And I'll give you some examples as well. The other very good example over here of what makes sense to put in a separate dialect are domain-specific accelerators. Now we talked about AI, AI-specific accelerators, or let's say some FPGA accelerators. And again, these you probably want to have them made from silicon experts that are experts in that area. It can be created to make a SKU which is targeted and tuned towards a very specific market segment, very niche market segment, which you don't want to put in your monolithic die. So you have that functionality separated out in a dialect, and then only for that separate specific market segment is when you put that dialect. So allows for a much better combination of chiplets that can cater to a different market segment. So again, a very good example where you can make the best use of this disaggregation technology to create very good product, attractive product solutions. Okay, now we come to the part where we are going to talk about the consideration. So yeah, we said that we wanted to disaggregate, and we have seen the pros and cons of disaggregation, and we've also seen some very good examples where disaggregation made a lot of sense. Now, what are the considerations that we need to take into account when we are thinking about creating a disaggregated solution? If we are the ones that are designing the SoC, if we are the SoC architects, what are the things that we need to take into account when we are disaggregating our solution? The first one, obviously, is the bandwidth. Now, once you have decided what is the technology that you are going to use for your die-to-die technology, what is your die-to-die technology, and let's say you've defined the number of lanes that's going to be there between the two dilets, that overall defines an upper limit of the amount of bandwidth that can go across the different dilets based on your technology and your number of lanes, which means that now everything else which is being partitioned in a separate dialect, if it needs to talk to the other main die or another dialect, that envelope, the bandwidth envelope is fixed. Everything has to go within that, has to be in that range. So if you see that, okay, the amount of information that needs to pass from one of the dialects to the other dialect is going above that, what could you do? What are the things that you need to take into account? One option could be, let's say you have a main die and you have your IO die in a separate dialect and you have a lot of information passing between the two. Maybe some kind of a decompression engine can help you reduce the overall amount of raw data that's passing. In general, raw data is going to be much more larger than any kind of a processed data. So any kind of a processing can help you, reduce the amount of overall bandwidth that's passing. One way could be, some kind of a decompression engine that can be sitting, and that can kind of reduce the amount of bandwidth that's going across. The other thing, let's say we talked about graphics dies or core dies that are sitting in a separate chiplet. Then how about having some local caches that can make sure that the intra-die, a lot of communication happens intra-die and only some amount of cache misses come over to the other die, to the, let's say, the main memory. So these things you have to design the caches accordingly so that your overall bandwidth, expected bandwidth between the core and the main die is within the limits that has been defined based on the die-to-die technology and number of lanes. So bandwidth is the number one consideration. I think we had a lot of questions regarding the latency. So obviously, you think about any logic setting in the same monolithic die that's, making an access, let's say from the CPU core going to the memory within the same monolithic die versus it having to cross a dielet, another die-to-die stack, and then accessing the main memory, let's say. So obviously there is going to be an increase in latency, which means that when you are doing the analysis of the overall latency of the solution, the end-to-end latency of the solution, you need to take into account the overall die-to-die stack latency that gets added. Now, what we have seen is that over the years, the overall latency addition of the die-to-die stack has become very less. In fact, the UCIe stack proposes about less than 2 nanoseconds of latency for each side of the stack. So maybe 4 nanoseconds in your overall end-to-end data path. But that needs to be accounted for. For example, your buffers, all of those things need to be, you need to add that additional latency in the end-to-end path to account for the buffering or the overall, the round trip delay that needs to be accounted for in your solution.
We need to involve any requirements based on qualified learning.
So overall, what you can do is that, see, generation to generation, the latency is anyway reducing. Overall, the end-to-end latency is anyway reducing. Now, I can give you examples of what the industry is doing is that we have seen very, very stringent requirements that are coming up for the die-to-die stack itself. So as to make sure that that adder is as low as possible. Now, obviously, anything you do on top of that on the SoC die or the base die or the CPU die, that's always going to help you. But the trend is towards making that adder so small, let's say a 4 or 5 nanosecond kind of an adder that can be easily managed with a couple of extra buffers here and there. So that when you are thinking of designing your solution, that does not play a big part in your making the decisions. That latency is kind of getting squeezed to the very minimum is what I would say.
And when you're saying that it's a natural technology,
Yeah.
We have added latency, and I have to look at power with it. How do you see the trend making the design today?
That's a very good question, actually, and more like an open-ended question almost. How do we see 5 years down? In fact, we don't even know what kind of new technologies might come up in the next 5 years.
When you're talking about, let's say, how do you start this? You want to start using.
True.
That's the whole point.
Absolutely.
I think that's going to be a bigger challenge there.
Absolutely, point taken. And I think all of us know that the maximum focus is on reducing the memory access latency, right? So you have to just put your best, ideas there to ensure that the memory access latency is to the minimum. The IOs probably you're okay to have them pay a little bit more penalty in terms of the latency, but the core to the memory latency has to be the minimum. And if your memory is in the base die or the SoC die, you need to ensure that that has the absolute shortest path possible. Again, it cannot solve the problem of 10 years from now, but yes, that is one of the challenges that we need to look at. Absolutely. Good question.
One more question.
Yeah.
It may not be a problem for, say, a 3D solution, but for a 2.5D, I believe you'd also want to do some kind of encryption when you're pushing from right.
Very good point. We have that just later in the slide, yes. So yeah, I'm getting through the considerations. You guys are already catching up. So the second point, I think Vishwajit also touched upon it, is the power consideration. But what I am looking at is from the point of view of this huge number of additional die-to-die PHYs and additional logic that you have now added in your solution, which was not there in a monolithic solution. In your monolithic solution, let's say this entire thing was a monolithic die, you would not have this whole bunch of these 8 additional die-to-die PHYs in the stack. And these are very, very high speed PHYs, like we talked about SRDs, right? Very, very high speed, maybe 16 gig, 32 gig level of PHYs. So they are going to consume a lot of power while transmitting, and even if they're not transmitting, the analog part might be consuming a lot of power, which means that a lot of thought has to be put into putting these die-to-die, some kind of a low power mode has to be thought for these die-to-die PHYs, which means that, let's say you are not using them, so you can power them off, or maybe you are not using them fully. Let's say your die-to-die entire link has a overall bandwidth of 100 Gbps, I'm just giving a number. Maybe you are only using 50 Gbps in a particular mode where you're in a low power mode. So does your solution have a way to reduce the power of the PHY by maybe turning off lanes or running at a lower frequency, so that your power envelope is still within control? Otherwise, even when you're not doing doing any heavy duty workload, your power is you're just burning power because of the PHYs that are there, simply because of the PHYs that are there, right? So which means that a lot of thought has to go into what are the kind of low power modes that you're supporting for your additional PHYs, especially when they are not fully getting used, when they are not being used to their maximum, let's say. I talked about the flows, and I think we had a question on what kind of flows that we need to think about. So any global flow, which is going in your original monolithic solution, you have global flows which were kind of going across the entire SoC. Now that entire SoC is partitioned among 4, 8, whatever chiplets. So all of these global flows have to be very carefully thought through and architected to ensure that they are able to work seamlessly across these tilets. I have a few flows listed over here. First one being the boot, reset, and power management. So now imagine you have these dilets, and in a normal die, you will deassert the reset, and all the different parts of the logic start coming up. Phase 1, phase 2, phase 3, whatever may be the solution or structure. Here you have independent dilets, and they might be coming out of reset at different times. Now, probably you don't want to have a very, very tight handshake between the two, because you probably want to have independent, smaller level flows for each of these dilets to come out. But for sure, before these two dilets start communicating with each other, there has to be some kind of handshake to make sure that both these, or whatever n number of these dilets, have come out of reset. So these handshakes, which were earlier not even required, have now come into the picture. So you have to think about, how do you handshake between the dilets when you come out of reset? How do you make sure that both the dilets are ready to start communicating? Now, boot strategy. Normally, I mean, we are only thinking about when you have all the dies aggregated together and packaged, final product, maybe you have a single die which is booting, and that's finally bringing out all the other dies. But you also probably need to think about when you are doing your testing, bring up, you probably need to have a mechanism of independently booting up these dilets so that you're able to test them, validate them separately. Don't want to be waiting for all the dilets to be coming out in different technologies, getting packaged together, and only then you start your validation. That's going to be pretty late in the game, right? So you need to have some kind of a strategy in place, maybe just for the debug part, where you are able to boot each of these chiplets separately and are able to validate and test each of these parts independently before you put them together. That's also going to be key in your HVM testing. In your testing itself, you need to make sure that you are able to test each of these dies together before you package them in one go. The other interesting part is the flash configuration. So most of our SoCs, we have these configurations or straps which are there in some kind of a flash device, right? Now, obviously in a monolithic die, you have a single flash, you're getting all the data out of the flash, you do some kind of an authentication, and then you distribute them across your SoC. Now you have these 10 different dilets. Obviously, you don't want the customer to pay for 10 different flash that are connected to each of these dilets, which means that you probably have a single flash connected to your one main die, let's say. Now there has to be a mechanism for this information which is being pulled out of the flash, all the strap and all the configuration information that now needs to go across these multiple dilets from the main die. And here again, we need to ask that question, do we need kind of an authentication? Because it could be some important configuration information that changes the skew of your die. Now, again, that depends on the technology, and your use case and your product solution, whether you need authentication for all of these, information, the config information that's passing across these dilets. So again, that is something that needs to be carefully thought of when you are passing information, critical key information from one die to the other. dilate to there. Yeah, sure.
But talk about patient safety. That will affect the performance because you talk about lots of handshaking, and if you just connect a single accelerator to the any chip, so if handshaking is involved, so it take the 100 nanosecond or say 1000 nanosecond, and it will ultimately, if the system, if you require a product that having the latency is very critical, then don't you think this kind of thing will affect the performance?
A very good question again. So there are two things that we talked about. First is the handshake. Usually the handshake is like a one-time process. For example, through a reset flow, let's say you do a handshake just to, or maybe during the low power flows, you do a handshake to make sure that both the dies are agreeing to go into low power, and then you do it. So the handshake is more like a control part that happens once in a while. Now, authentication, there are two parts to security. We'll talk about security also. There's authentication and then there's encryption. Authentication means that whatever information that you have received, it is coming from the correct source. Let's say I'm authenticating whatever you sent me. For example, if I got some config data from the flash, I want to make sure that the data is provided by the correct source. It has not been tampered with, let's say, right? You want to authenticate, there must be some signature check or something like that, right? But again, that's also one time, because configuration, you'll read one time from the flash, whatever is the overall, the configuration of your die, you read one time. So authentication is still one time. But if we say that we need to encrypt the data that's going across the dice, which is more like a security, and we'll talk about that also. Encryption is something that might come in the data path. Because there what you're saying is that, let's say I have this very critical information that's passing between these two dialects, so that I don't want anybody to be able to probe even through the package. Again, that's also another question that we need to answer, whether it's whether my technology is such that nobody can probe through my package, or maybe they can. So then, and what kind of information is passing through it? Is it critical information, very, very crucial information that I don't want anybody to handle in any case? So then I have to encrypt the data path, which is definitely going to add latency, I agree. And that is something that you need to bake into your solution. If it is that kind of data. Again, you can separate out, you can say only this key information, maybe I have this Netflix account detail that's going between the chiplets. I don't want anybody to access that. So maybe only that part I'll encrypt. But the rest, maybe I don't, maybe I do. So that depends. That's your product kind of a, your product solution you have to understand. But definitely if you add encryption, it's going to add latency.
As you are depicting the case where the data is between the through the die 1 only, die 3 and die 2, is there any DMA kind of solution so data latency could be the
Absolutely. I mean, data latency, like I said, latency is one of the key things that we need to think through, right? Absolutely. I mean, all kinds of innovation and bright ideas. I'm sure the industry is going to invent more and more of these things. How to squeeze the last bit of latency out of the entire path. Absolutely. Here, in this case, we are talking about a configuration data, which is one time. Like a flash data, you're booting up, you want to understand what is the configuration, the basic configuration. What are the modes that are supported by your chiplet? You fuse off certain things.
It's a kind of setup thing, and
setup thing, yeah. So
the other thing will be done automatically.
Exactly. So again, even the boot times are important these days. So we are thinking about reducing even the boot times to seconds, maybe maybe less than seconds. But that is just one time. When we talk about DMAing things, we are probably talking about the data part, where it's like a runtime thing. You have huge amounts of data coming in from your PCI I/O. You want to shift it to the memory or some other accelerator. That's where you want to talk about DMAs and optimizations there. Yeah, so the last point we talked about a little bit, like the low power flows in the power states also needs to be synchronized. Obviously, you cannot have one dialect which has gone into low power mode and the other dialect is still trying to access data from the other side. So obviously, any kind of a power state handshake has to be done by a handshake before both the dies decide to go on a low power state. Security, again, something that we talked about earlier. The main question that we need to answer is that what is the kind of asset that I'm trying to protect? Can unencrypted data flow between my dialects? What is the asset that I'm trying to protect? So that's the question that has to be answered by the security architects, let's say. And we also need to understand whether here we are only talking about a physical attack between the dialects. Somebody who has physical access to this chip is when they can do the physical probing. It's not talking about, we are not talking about a software kind of an attack. Here talking about a physical attack. So we need to understand what are the attack vectors that that this product needs to be built against, or with that backdrop. What is the technology we are using? Is it possible? How easy it is to probe and probe the data between the packages? What is the use case? What kind of a data I'm putting over here? Is it critical data? Is it confidential data? Then and what kind of assets I want to protect? Based on these questions, we might have to then decide whether we want to do encryption. And encryption itself is a huge topic, because it's not just about the original, like we talked about data path encryption. But before you even enable the data path encryption, you have to exchange keys. You have to make sure that the keys are not tampered with. Nobody can, reverse engineer or figure out what the keys are. So they're it's like a whole world in itself. So if your product definitely needs some kind of an encryption story, then a complete security planning has to be done for that product. So right from the very beginning, from the key exchange part till the additional latency in the data path, that needs to be accounted for. Debug. Yes, again, I think Biswajit also talked about a little bit on that. Now, first of all, we have to think about debug from two things again, like similar way we talked about the other topic as well, like for the boot, for example, that there are two types of debug now. One is once your product is already assembled, it has been packaged, it has been shipped to the customer, then you get something back from your customer, some issue that you need to debug. Obviously, at that point in your product, you will only have a single, let's say, single main debug point, let's say a USB stick or whatever USB path through which you can debug your entire chiplet. So there has to be a path that has to be there from the main die to all the other dielets. You don't want to be having multiple debug ports or points brought out on the package. So that needs to be there. But prior to that, when you're debugging in your own labs, in your own company, in your labs, you want to be able to have the ability to be able to debug the independent dielets, right? So independent debug of these dielets is also a key factor that needs to be factored in. Both independent as well as a unified way of debugging the entire solution, because when it's packaged, it's gone to the customer, you don't have all of those ports coming out. So you need to have a unified mechanism of debugging all the different dielets through one main die, as well as you need to have an ability to modularly debug each of the independent dies prior to shipping and packaging. So like we said, all global flows, we need to have a very, very clear, well-defined strategy before we, take on this journey of disaggregation, especially for all of these global flows. A lot of thought has to go into, into the baking of all of these flows prior to even us, starting on this journey, let's say. All interfaces, protocols, handshakes across chiplets have to be defined. So what is there apart from flows? What about verification and validation? Now, like we can have any protocol that we want that allows us to talk. Eventually, what we want is that we want some data to be going from one dielet to another dielet. That's the overall aim. We can have n number of protocols that can do the job for us. If it is a standard, well-defined protocol, it makes the life of the verification engineer, of the validation engineer, much simpler. You can get standard BFMs from third-party companies, or you can write your own, for example. It allows you to independently validate and verify each of your chiplets. You don't have to wait to put them together in the SoC overall, scheme of things to be able to validate these interfaces. So obviously a well-defined, I think all of us will agree to this, having a well-defined interface goes a long way in closing the verification and validation flows. And yes, standard interface allows us to have a much easier verification and bring up. Another thing, a key thing is the reliability and survivability. Now we talked about these die-to-die lanes, which is allowing us to talk between these two dielets. So again, this is going to be like really high speed. Again, I'm talking about now and 5 generations, or let's say 5 years from now. Obviously, it's going to become higher and higher in frequency and bandwidth. How are you going to ensure that the data is faithfully transferred from one dielet to another? Especially if your core is fetching some data from memory, it can be an instruction. Imagine that getting corrupted, you have no clue. It'll just go haywire. So there has to be some amount of data protection in terms of, reliability, like any kind of a CRC, any kind of a parity check, ECC, that needs to be built into your protocol or your solution. You have to think through it. Like, what is the error rate that I am looking at? What is the fit rate that I have to, work towards? Do we need to enable packet retry? I mean, is it required for the kind of speeds and frequencies I'm looking at? Do we need to enable some kind of a packet retry mechanism? What about lane and link repair? Let's say you have 32 lanes, you have, I don't know, so many of them, 32 into 10 lanes across your entire solution. What if one lane fails? Are you going to throw away the entire chiplet? Or maybe there can be a mechanism of a die, kind of a lane repair or a link repair, or maybe a redundant link or a lane. So these things, again, will go a long way when you finally want to come up with a reliable and stable solution. So with that, we come to the what of disaggregation. So we looked at all the different flows, the global flows, and what are the considerations that we need to take into account when we are trying to architect a disaggregated solution. On the what side, I want to talk about UCIe, which is the Universal Chiplet Interconnect Express. The open specification 1.2 was released in May 2022, actually. These are the board numbers, all the who's who of the industry is listed over here. And the idea over here is to be able to create an open chiplet ecosystem. Like we gave an example of chiplets coming in from different vendors. That is only possible when both of these chiplets are talking the same language, right? They're talking the same protocol, they're talking the same terminology. And that is what this UCIe is. It is a protocol which talks about the die-to-die, die-to-die technology in terms of the PHY as well as in the link layer. So this is what it covers in the 1.0. It covers the physical layer, the PHY, with the die-to-die, and it has industry-leading KPIs. We'll have a look at that in a couple of minutes from now. On the protocol side, it supports PCI and CXL. So now you can think that earlier all your accelerators and additional die-to-die, no, not die-to-die, but let's say your additional solutions that you were building with your overall SoC, you were mostly connecting your accelerators over a PCI lane or a CXL lane. So here it allows you to have the same solution, but now within the same package, which means that your protocol layer remains the same. Whatever additional logic you had remains the same. You just replace your PCI PHY and that area with a die-to-die PHY or the UCIe PHY, let's say, and the link layer, and you can have the entire solution in a single package. Currently, this is what is already included in the specification, CXL and PCI. Going forward, there is a plan to add additional protocols, which means that any of other protocols can also get included, and you can build your solution with any of the other protocols that gets added into the UCI specification. Even now, it has a mechanism to tunnel any protocol. So there is a PCI, there's a CXL, and there's what is called a streaming protocol, which means you have whatever your protocol, AXI, whatever, you just push it through the streaming interface, and then that becomes your protocol. So a protocol has been defined which allows the UCI to become like a tunnel where you can push in whatever data you want to through this stack. So some of the things which are currently not covered, which will come in the later versions of the specification, the form factor, the management, the chiplet management, for example, these things are not yet covered. So currently, like I said, these are the two things which are covered. The physical layer, the die-to-die PHY has been defined. The protocol layer, CXL and PCI, has been defined, and the streaming protocol is there, or the streaming mechanism is there where you can stream whatever protocol that you have through. And these two things which are currently not covered, expected to come later. So this is a quick snapshot of what it is covering today. So PCI Gen 6 onwards and CXL onwards, we have moved to a FLIT-based kind of a mechanism, and that is what the UCI protocol builds upon. It has something called the FLIT-aware die-to-die interface, FDI, and the raw die-to-die interface, RDI. So all protocols like the PCI Gen 6, CXL 3.0 and 2.0, and the streaming, all of these protocols come in a FLIT kind of a format with the CRC attached to it, which takes care of the, the protection part as well. And that can be pushed through the die-to-die adapter, which takes care of the CRC retry, link management, initial link bring up and protocol parameter negotiation. All of that is handled by the adapter. And then the PHY layer, which takes care of the training, the power management, the link bring up, scrambling, lane reversal. So the PHY, the die-to-die adapter, and the initial protocol layers. These three things have been originally defined in the 1.0 specification. It also, the physical layer also has a main band and a sideband. So main band is there for the main data path, while the sideband has been created for any kind of a handshake or any kind of a exchange, any sideband exchanges. So for example, you might have seen, right? I mean, when you connect your die to die, let's say the one person is looking at 0, 1, 2, 3, and the other person is looking at 3, 2, 1, 0 kind of thing, right? So mixing and matching, like which lane is connected to what, right? When you connect these two. So that's the lane reversal. A quick snapshot of what are the benefits of UCI, and you will see that it kind of takes care of a lot of challenges or considerations that we had talked about earlier. It provides a standardized interface. We talked about the RDI and FDI. It has a very well-defined software view and discovery similar to CXL and PCIe. So it allows your software to also discover how many die-to-die links you have in your product, because it can change from SKU to SKU. So you can have your software stack discover all the different links that you have in your solution. It allows for power management, has power management features. So you can put the link in a low power state. They have two different states, L1 and L2. L1 is the shallower state, L2 is a deeper state. You can just power down your PHY completely, turn off the clock, or you can power gate your PHY so as to get the power management power, better power, numbers. It has a very well-defined parameter negotiation for easy interop. Like we said, one chiplet has only only supports up to a particular frequency. Another chiplet supports up to a higher frequency, which is the next generation. You have a way to handshake and negotiate that while bring up, and you can actually choose the frequency that works for both the dies. It also supports optional CRC, packet retry. It also has something called the link runtime link parity, which allows you to debug which link might be kind of the one that is giving you a most number of errors. So it is a link or a lane level parity. So it allows you to, it gives you an idea of which lane is having the maximum number of failures, because in a CRC it's a packet wide is a correction. So you don't really get to know which particular link is causing the error or issue. It has a lane repair with an advanced. So there are two flavors of UCI. There's a UCI advanced and UCI standard. So it supports lane repair and with degrade, both of them. One with UCIA and the other one with UCIS. And like I said, it has a target latency of less than 2 nanoseconds for the adapter and PHY. So the one side of the stack is expected to take less than 2 nanoseconds, which means that we have already squeezed it to the bare minimum in terms of latency. Yes, active mode latency, absolutely. Yeah, it's like barely anything. That's true. Yeah, true. So here we're only talking about the active, like when it is in full bandwidth, full frequency. Obviously, that's when we're talking about a 2 nanosecond. You cannot be running it at 4 megahertz and ask for a 2 nanosecond latency. So yeah, this is kind of giving a quick snapshot of the advanced and standard packages. Okay. So in summary, I think we are all agreeing that the industry is moving towards greater and greater amount of disaggregation. We see that happening all across us, multiple products from different companies. However, it is not just a cake. I mean, not a cakewalk. Let's say there is a lot of consideration, a lot of thinking through has to happen before we, decide to move in this direction. And we have to define the right strategy for our product, what works, what makes sense for our product, our market segment, our solution. And standard interfaces such as UCI definitely offer us a quick jumpstart, which helps us get the most out of disaggregation. Okay, I don't know if we have time for Q&A.
Let's break for
Okay.
10 minutes and then come back.
Sure.
And along.
I know.
Almost.
Yeah. Tea is ready. Tea coffee is
ready. So we'll take 10 minutes and we'll come back at 3.
1 hour we have, so
45 minutes. 3:30. Okay. We'll come back at 3:30.
So 40 plan was there. I was to build 5.
I was just making Sure. Please call me Debolina.
Sorry, MD5 from CDAC. I just had one question. I came across a recent technology of C6 2.2 that we talk about C6 over CXL. We talk about low latency and all that stuff. So in this, the third mode of operation where we say like using streaming protocol can accommodate user defined.
Yes.
So can we go forward with C6 2.0? and
Absolutely.
implement
Any
it?
protocol can get through. Now, what you need to, in fact, I am aware that there are certain ECNs which are also coming, in the next generation of specification, maybe very soon. So in the streaming mode currently, which is defined in UCI, in the current UCI streaming mode, the adapter does not take care even of the CRC or retry. So that has to be taken care in the protocol layer itself. I think C6 already has a CRC set. So if that is already there in your controller, nothing to do. Simply connect it with the adapter over a FTI interface and you're done. If let us say you want the CRC and retry to be handled with the adapter, my understanding is that such an ECN, an electronic change notification, is coming soon. So that part also you should be able to kind of offload to the adapter.
It is stated like UCI has its own dedicated file. Is it possible to, because like C6 and CXL is built over the PCI?
Yes.
So is it possible to integrate it with the existing PCI file?
See, the problem with using the existing PCI files that you'll not get the power benefits. The PCI is meant for over the PCB or a separate chip, packaged chip connecting over a PCI connector. So that requires a lot, that has a much higher power.
So the advantage
Here
of
you're in a
these
single
protocols are not.
You're in the single package, right? You don't need that amount of, you don't have to throw the single to that level. You are in a single package, so you can reduce the power significantly if you use this file. You can definitely do that, but you have to pay the penalty.
Thank you. Excellent.
Thank you. Okay. I don't know if we are allowed to share our details.
The LinkedIn profile, if you have.
Debolina Shakali. Just search my name and I think you'll find it.
Yes, so I have a doubt actually. So we know that in-memory compute, a lot of research is also going on in that end. And when we compare this with that, there's no much flexibility in memory compute, and I guess the research would be slow in that domain. So do you see that this as an intermittent solution for those problems which they are dealing with?
See, in-memory compute is
Bringing memories closer to the processing.
more like bringing compute inside the memory.
Yeah, that is, yeah.
So the idea there is like you talked about, right? When you send raw data from one part to another, there's a lot more data. Instead, the idea of in-memory compute is why can't I do some part of the processing there and then bring the thing out, right?
Okay.
That's the in-memory compute idea. That
No, you just, yeah. Not fast.
Hello, hello,
Can I be here?
hello. Hello, hello, checking. Hello, checking.
Hello?
Hello.
I'll be confused.
Hello? Hello? Hello?
Yeah, we can hear.
Can you hear? Can you hear?
Yeah, Rupesh, we can hear you.
Okay. Okay, good. Can you hear me?
We'll start gathering in a few minutes. I said 3:30. It's a few minutes over.
He's there and he's getting it. Maybe probably I don't know people from that team, so because of yeah. A lot of people are there because I have two. Oh, let me see. So, I don't know the interesting is something.
Okay, this should. About 40 minutes. So we'll have to take 20 minutes to motion. Sure. Many questions on the bio.
I'm just seeing the time and I'm looking at it that I should last second.
Most questions which are.
4 o'clock is
40 minutes.
Good afternoon, everybody. We'll start the session shortly. Rupesh is ready. We'll have questions towards the end. We'll have about 10-15 minutes for questions. This is the third section of the talk today. Rupesh, all over to you.
Thanks. Can you hear me? Can you guys hear me? Okay, so Biswajit talked about the technology and some of the technologies are already in the or created by the products and so on, right? And Develina talked about the architecture perspective. How are we going to create the cut lines? You know, what do we need to think through, right? When we are considering that architecture. It's not clear. This side. Is it better?
You might have to increase your, actually. This. Can you?
Hello? Yeah. Is it better? Yeah, so I think
let's say we have an architecture, we have the technology, we have the packaging technology, we have a process technology and all that, but we still have to design the chip, right? And healthy chip, right? So for that, we need like tools, flows, methodologies, maybe work model changes, maybe like certain standards which we have to create because this is a new ecosystem, right? We need to create those standards. Otherwise, we'll not be able to create that healthy product. So that's what we'll talk about. I'll give you some examples of why those are important, right? To create the chiplet product and heterogeneous integration product system. So to enable the heterogeneous product design, we need multiple chiplets, right? It could be on different foundry, different process nodes, and maybe you're choosing certain process nodes for certain specific designs so that you can optimize them, certain specific process nodes for certain IO kind of configurations where you can optimize really them, and so on. Overall, looking at the system view perspective, right? And you need process as well, right? When you might go from one process node to other process node as well. That's also advanced process node is also very critical because you're looking at from overall system perspective to enable a better performance, better power, better product for the ecosystem, right? So, and of course, we need advanced package technologies, right? Along with all these, we also need to think through how the power delivery we're going to do, how the thermal challenges, all that also has to be considered while you're doing a product design using heterogeneous integration, right? So Vishwajit talked very detailed about this particular slide. So essentially, we started off with sea of transistors way back, and now we're talking about all chiplet ecosystem, right? And it could be like, I have a plug and play from, I already have an chiplet existing. I can just use it, reuse it, and create a product out of it. I can just do faster market, right? Faster time to market and so on. For all these, we need like, the whole collaboration, right? Across EDA, IP, the foundry and fabless ecosystem. Because without that whole pieces together, we will not be able to build a product because we won't be able to think through that, right? Because how do you think about a connectivity from one chiplet to other chiplet to other chiplet, right? It's very difficult to visualize and so on. So I think that's why it's important that collaboration, the co-design and enabling the tools methodologies, and you could have a one chip designed in one side, other chip designed in other side. How will these two talk to each other, right? It's at most important compared to what was happening before, right? So, and hybrid bonding, and Biswas touched upon this hybrid bonding a little bit in the sense that, okay, let's look at this particular picture. We have standard packages where the bump pitches were like 100 microns bump pitches, right? Where bump density was about 100 bumps per mm square, right? When you go to EMIB, which is 2.5D, we call it, and the bump pitches are scaling down to like 55 to 36 micron bump pitch, where you can get more number of bumps per mm square, right? And similarly, in 4 rows, Lakefield was one good example which Biswajit gave, right, where the top die and base die both were active dies, right? And there, you have about 50 to 25 micron bump pitch, where you could have a lot more bump density per mm square. But when you get to 4 rows direct or hybrid bonding, right, where you have a technology where bump pitch can scale down all the way close to less than 10 microns, right? And in that such scenario, you have like bump density 10,000 bumps per mm square, which was never heard of before. So those technologies are coming across going forward. Now that means there are a lot of connections between the first floor to second floor, or first floor to ground floor and all that, right? There is a lot more bumps talking to each other. That means a lot more connectivity is going on, right? So what it gives us an opportunity, if you look at this particular picture, when we go from bump pitch scaling down, it's just like how we do regular wire in monolithic SoC, but in 3D, you're just having the same wire because you're getting into nano micron bump pitches, right? Sorry. Yeah.
The technology part of it, or is it also some circuit and other?
It's mainly the technology part of it, but there are some innovations in the circuit as well to enable that as well. But this is purely about technology.
What's it last to? What's different that allows?
From the 4 rows to the 4 rows direct. So it is essentially the type of material what we use, which is kind of helping you to get there. It's maybe like copper to copper connection, as Bisu was talking about. When you go to hybrid bonding, it's like you're connecting from wafer to wafer, just like a wire running from top to bottom. There is no micro bump there actually, right? Bisu, you want to add anything?
Yeah, so basically, if you look at it, right, standard micro bump sandwiching is usually a assembly line process. And if you wanted to sandwich these two together, it's an in-fab process. So let's say I have two fab units. In one fab unit, you are producing 20 nanometer node. Another fab unit, you are producing a 10 nanometer node. Now, you will carry the silicon from one fab to the other fab and then create a sandwich. So it's a little process and operation wise difficult to coordinate. There is some logistic extra cost involved because these two need to be perfectly synchronized. Well, on the other hand, the microbump technology, which is an assembly line process, you in the two fab line, you create two up to microbump. You sit this to an assembly line, it's a package house, and they just create a sandwich.
So the last one was
Yeah, so this, yes, the progress direct what you take it, that is basically there's no microbumps, direct connection.
So direct copper to copper connection.
Copper to copper connectivity. It's an HPV. Yes, it's kind of a directly hybrid bonding. Yes. And if you look at this one, the Foveros one,
You have a micro
that is basically a microbomb structure is there. It's basically a 9 micron, 10 micron radius kind of a copper, which is overhang is there. So you directly attach in assembly line, you can attach them very well. But while that one, there's no height practically. So in the diagram shows like slight height. It's like kind of you build them under the pressure in fab process, you can only do that. So that is a more costlier one and advanced progress direct one. And there the beauty is you can go to the microbump pitch up to 2 micron, 3 micron, 4 micron. Right now, industry is moving towards less than 10. But technically, there is a path to go to even 2 micron, which is the same as your top most metal layer, AP layer pitch. That's the beauty you get. Package. So package on package, you can think about you make a one package, and on top of that you can make one more package. Pop on pop, you can take right. For memories you will have the memory package and another package. You just keep one on top of each other. Make the connectivity. That's again an assembly line process. Assembly line process, but progress direct is essentially. I mean, Intel is offering, TSMC is offering. They may call it a different code name, if the code name aside, but fundamentally they're a similar technology.
So, okay, so now you can imagine when the bump pitch scales all the way close to, like, as Bisu is saying, less than 10 microns, now the current industry is trending, and there's a path probably going down as well. Now you can think about it, right? That you can have IP or IP content itself, some portion of the IP content in one of the die, some portion of the IP content in another die. In a monolithic, you're going to construct them like this, right? It may be a big IP like this. Now you're constructing them like this. With the same, the wire lengths are going to drastically reduce here compared to you're going to build a monolithic die. So that is the beauty of it. You can just think about the number of opportunities we could potentially have to create such a designs. You can just think about it, right? So similarly, just you can see here, it could be IP on IP or macro on macro. It could be like IP folding, as I was talking about. You can fold that IP in two different technologies, and you could have circuits slicing as well. As I was saying, some circuits you can put it on the top, some circuits in the top, down of the same design, right? So so that's the advantage it's going to give us, and also there are multiple challenges. And as you can see, there is the silicon could come from different foundries, right? And how do you stitch all of them together onto one product? Is it really possible, right? Even today, to design in the same foundry, there may be multiple challenges with the chiplet ecosystem. But coming from different foundries, think about it, right? It's going to be multiple challenges. This is where we need to kind of create that work models, the standardization of things. Let's say today I'm developing hard IP. I'm delivering it to a customer. They're going to pick it up. I'm delivering some standard models, standard documentation, standard things, standard, so that they can integrate it, they can verify it and do a taping, right? So, but those kind of standards has to come in as well into the chiplet ecosystem as well. That's a critical point I want to kind of highlight. So let's talk about multi-physics design flow. So to implement, right, I've divided into 3 segments here. One is the early design, right? How do you do early design, early planning, and identifying the issues upfront? That is very critical, right? So earlier we used to have a chip, we used to give it to the package team. Maybe they just do the package routing and done with it, right? They do the simulations and so on and deliver. But now we have to have tight partnerships, right? When we're designing or floor planning a chip, we need to kind of talk to the package team, talk to the product team, and whole collaboration has to be together to create the better product and healthy product, right? So that's why that early planning and optimization at the early phase at the top, which is very important. The second one is implementation. When you're implementing, also considering the other factors, what is the parasitics of the other die? Considering some of those things upfront in your design is also extremely important as part of the implementation. And the last one is sign off. How do you do extraction of all these different parasitics of different technologies, right? How do you do thermal analysis, right? How do you predict the yield? How do you predict the cost of this particular overall product when these chiplets are coming together, right? Viswajit was giving a good example of Ponte Vecchio, right? 46 chiplets, right? And there could be, 100 plus chiplets in the future, right? How do you create all that, put all the chiplets together and create a healthier product, right? So that's why I think what I was trying to say is that early planning, implementation, and sign off. All the tools, flows, methods, what we have today may not be scale up to this particular technology. We need to kind of refine them. We need to collaborate at the industry level to create the standardization, create that work models. So I can probably skip this example. It's similar to what I was talking about. So now we'll talk about next couple of slides about co-design, and why co-design is so important. And also we'll give you 1 or 2 product examples of how the co-design kind of help to create a good products, right? So if you look at a traditional co-design, as I was talking about earlier, right? We have an SoC or a chip. We're just designing it independently. At very high level, we probably know, hey, these are the IO components, and we tell the package team, this is where we're placing, right? So then we give it to the package and they do the interconnects, they do the analysis and give it to the platform and so on, right? That may not really, we did not have to do so much of co-design earlier, right? Now, with the heterogeneous components coming together, it's extremely important with the co-design, right? Co-design with package, co-design with platform, where these components are getting placed. Even when you start off with a floor plan, that itself, we need to start off with a mindset of system level view. Where how do you do partitioning, right? Which component, Jabalina was talking about, which component has to go where, right? So, and where they are being placed at the package level. So those are also extremely important. So that's why this co-design is becoming extremely important for us to make a better products, right? So if you look at here, as I was saying, there's a process technology, process scales, and also we have an advanced package technology as well, all the way till 4 rows direct or hybrid bonding. But putting all these pieces together is extremely important, and to get a better optimized product cost, performance, and also to meet schedules, right? If there is an issue which we identify late in the game, it could have been very difficult for us to fix that if you don't have an early planning, right? So that's what we are trying to talk about, why co-design is so important in chiplet era. But there are challenges with co-design, right? It's not going to be easy, right? For example, different set of tools we use, right? Maybe one chiplet is using some tool, the other chiplet is using different tool. How do you integrate all these tools together? How do you integrate all these different chiplets together, right? What is the data exchange format? How will I exchange data to you? How do you give me? How do I know whether I'm putting the pieces together correctly or not? Connectivity perspective, right? Or from the timing perspective and whatnot, right? So those are some of the challenges we have in this ecosystem today, right? And also, how do you optimize? How do we co-optimize all the way from, let's say we have IO sitting one place and that connectivity go from two different dies. And as Biswas was showing one example, right? IO is in one die, but that connectivity goes all the way from interposer die, package, PCB, and so on. How do you extract the whole piece and make sure that it is still meeting our signal integrated requirements? Right. So that's why it's becoming extremely important, but there are challenges as well, is what I'm trying to highlight here. And we were talking about the rule decks as well, right? You know, when we assemble all these different pieces, how the micro bumps are aligning together, or how the copper to copper bumps are aligning together physically. How can we predict that, or how can we analyze that alignment upfront in our design cycles, right? So that when I deliver a chip to you, I can put them together physically in the assembly process, right? So those are also that standardizing that design rule text. We can have the standard suite, what rule we are passing to the tool, so that when we bring in the chips, can we verify them upfront before we put together, right? So that's why EDA tools has to mature, right? To support this overall ecosystem, right? Where do we draw the physical cut lines, and how do we, what are the design planning, right? Even floor plan tools probably has to mature, right? The package guy should be able to see which block is where with respect to the whole package level view. How am I going to connect this block to here, right? Let's say if I place the block in a different location, I'm not able to route. He should know upfront. Right? So that is the granularity, which was not required before. Now it is required, right? So I talked about the multi-physics, right? The thermal challenges, what we talked about, mechanical challenges, what we talked about, what are the electrical properties of one die need to be brought into our simulations so that we can see that whole picture together, right? So the bottom line is design optimization includes architecture selection, the way the cut lines she talked about, the package architecture selection, right? And the process selection and overall form factor, because there are certain limitations for the product as some customers might have. They wanted certain X, Y, Z from the package standpoint, right? All those things has to be considered. And routability, routing estimations, right? Initial part of the design, do you have the complete routing? No, right? It's not realistic, but you probably need to go with some estimations. But can that estimations be too off? Then it's not going to help us, right? So the tools flows has to be, estimating based on whatever the technology pieces information what we're able to provide. It should be able to estimate that, right? Maybe when we're designing a monolithic chips, we already probably have that type of infrastructure today, right? But we have to build that infrastructure to scale up to that chiplet ecosystems. So here, again, a similar example, the standard format of data exchange is extremely important. If you just look at this particular flow chart, the gate level design, then we do partitioning, blocks where, which block has to sit where, and so on. Then chip package floor planning, as I said, is extremely important, chip level floor planning and also package level floor planning and system level floor planning as well. Then we kind of do timing analysis and, the electrical analysis and so on. Then we have all these pieces coming parallelly, right? There could be multiple chiplets. There is a package design. All of them are, converging at similar time frames. So that way, you have a converged final heterogeneous system, right? Here is a example of floor plan, right? As I was talking about, you might have a number of floors, right? First floor, second floor, and so on. But since the power is going from ground floor, because package is the one which is talking to the ground floor, and how it is going to the top floor, right? What are the different components are there in the ground floor? So that, let's say if you put a high power component in the top die, and if you put a similar high power component in the base die, how will you really do the power delivery? There may be thermal hotspot right there, right? So you have to kind of coordinate and make sure that these pieces are kind of looked at in a 3D manner or a multiple dies together manner as well, right? So here is one good example I wanted to show how the code design kind of helped AMD come up with a good chip, right? So if you look here, there are the CCD dies, right? There are multiple CCD dies, and they need to talk to the IO die, right? Now, in the previous generation, they did not stack it like this. They probably had like, 4 chiplets, let's say, right? And they were directly talking to the IO die. You have a path directly in the package routability from CCD die to the package, IO die, right? The next generation, they had some more chiplets, right? They had 8 of them. Now, this particular CCD die, how can you talk to the IO die? They had to have the package routing traces coming through one more CCD die and talking to the IO die, right? Now, this was not done before. Now, there may be some active components right there, right? As they were showing here, right? So you have this is a CCD die, you have cores here and you have L3 here, right? Now, all these traces are running through that L3, right? So you need to consider the power delivery aspects of it. Earlier power delivery was smooth, previous generation. But this generation, if you don't co-design, right? Let's say you put a core there, it's a high power consuming IP, right? Then if you do the package traces right there, it's not going to really work out from the performance perspective, right? So that's why it's extremely important that there's a clear example of co-design importance, working with the floor plan, working with the package, working with the routability and all of the pieces together, power delivery, signal integrity, and power integrity, all those pieces together to make a product out of it. And also thermals, right? So thermals perspective, I'm just showing you one example here. So thermal crosstalk, you need to know what is next to it, right? Maybe this is creating a crosstalk on this die, right? And some of the dies coming from different foundries, different process nodes might not be the same height, right? Their thickness, their height might be different, right? So all these even mechanical pieces also has to be considered now, right? What is your neighbor? What is, below it? What is above it? All of that pieces has to be looked together. And again, materials has to be continued evaluation, continued innovation to solve some of these thermal challenges. Yeah.
Yes, it seems to really integrate all around the back. It covers much more portion.
Yeah, probably some of the materials has to be thought through in that angle as well. But having said that, all these chiplets are within the package, right? And they are one on top of each other, maybe differently stacked and so on. Maybe the thermal hotspot is within that region itself, right? And it may not be able to spread out to the package itself. So those are some of the scenarios we need to think through as part of the thermal design, right? Does it answer your question?
What do you classify as a hotspot? Like, what is it about?
In the sense that threshold meaning current density. If you have a large current density in one specific region, and and if you are not able to spread that, power out, that's what I was trying to talk about the hot hotspot. So it depends on product to product. You cannot just set one specific example. Vishnu, do you want to add any specific?
If you see most of the commercial grade process today, it support up to theoretically most of the commercial grade process, if you look at it, they support up to 125. They say you reliably can design up to 125 degrees centigrade. Now the question is whether you want to allow up to 125 because your existing thermal solutions maybe get broken there because your leakage of the devices will go high. So most of the design house where they wanted to do it to meet their overall power target, they restrict to maybe about 85, 90, 95 C. So you may call 95 C and above as a hotspot. I, for another application, can say that 80 and above is my hotspot.
Because above 80, though theoretically devices are going to burn out, but I will be above my leakage target. So it's depend on the design style what Rupesh is trying to talk through. And it's based on your type of design, type of application. Let's say you are running a laptop. You don't want your lab temperature to be more than 35, 40. Now, same chip, if I'm using it for some server, think about that. Yeah, temperature conditions are different. So this thresholds depends on case by case. All he is trying to say that look, whatever temperature you are defined, above that is a hotspot.
Exactly. Okay, so we're talking about the models and the standards, and some of these work is already happening, right? So there is a open compute where the industry experts coming together, trying to define a standard data exchange format. As I was talking about earlier, how important data exchange format is going to be to enable this chiplet ecosystem, right? So that's why they are creating, leveraging the existing standards, trying to create those models as of today. And today they are enabled it for 2.5D, right? And they're going to extend it for 3D eventually, right? So if you look, okay. So I think I was explaining during the break to someone, right? So the 3D is typically, right? You have one die on top of each other, and there could be multiple of them, right? That's in a 3D. So the 2.5D is that you can do it in multiple ways, right? So you have two or more chips in a package. How these are talking to each other through high density interconnect, right? One could be EMIB, Intel EMIB technology, where you have high density interconnect like a silicon bridge between the two dies in the package, and you have a high density interconnect between them. That's called 2.5D. Other way to look at it is some people also call 2.5D with the interposer die. You have a big interposer die. You have multiple chips on top of that interposer, right? And that interposer is used to do what? Two things, right? One is to do a high density interconnect talk between these two dies or multiple dies, and also to do the micro bump, which Biswajit talked about, to the C4 bump conversion as well. That's what the interposer is doing as well, right? So you still have a stack there in the 2.5D. Yeah. Some cases, it depends on how they look at it, but some cases that you can also call it as 3D there, but they're calling it as 2.5D. But yeah. You want to add anything? Or?
So good. So basically, just to be more definition, if you define, there is an active device between both the dies. Then you call as a true 3D. If there is a interposer, that basically means you are not fabricating active devices. And on the top of this, you have active devices, then you call as a 2.5.
Again, it depends on the application.
It depends on the transistor type what you use. If you are using a passive, let's say the leg field what we show their example. They have a compute die and the base die, and both of them are an active die. There is a processor in the base die, there is a processor in the top die. So that is basically a true 3D SoC. Okay. Now, if you look at 2.5D SoC, where I have a two die, active die at the top, and below I have just a connection in the die, but there's no device there. That people are calling as a 2.5D.
But I think it depends on the definition you give.
Fine tuning that comes
correct. Because someone was asking me during the break that, hey, there was one paper somewhere there were some devices there, repeaters mainly. They still call it as 2.5D, right? It depends on the person who's looking at it, right? So as I was saying, they're leveraging the existing model so that it'll become easier for industry to look at it. So for example, physical, mechanical IO, how do we exchange the data, right? They're looking for GDS view, left view, the SPICE. All these are familiar technologies for us already, right? They're trying to leverage that type of things to build that, right? And power integrity analysis, CPM model. Chip power model, right? As one of the standard, which people have to deliver. So now what, when I'm getting a hard IP for me to do an SoC, I need to do health checks, right? I need to make sure that is hard IP meeting to all these criteria, model requirements. Is it coming up with the right quality or not, right? Same thing, even here, we need to extend that, right? When I'm getting a chiplet, I'm trying to integrate, right? I need to make sure that I have a list set of standard models which are existing for me to do early analysis, right? Maybe the model, whatever they're trying to deliver, may not be mature enough that particular milestone. But eventually, when you go through multiple milestones, it has to get matured, right? Just like how we do convergence at SOCs, right? So first thing is standards are getting created, already there for 2.5D and continue to evolve for 3D. So let's look at all of them together, right? To enable this ecosystem, right? Few critical things which we talked about, the core design, the floor planning, early analysis, how do you, accuracy. Accuracy is also important because what you see in the simulations, you don't want to find surprises in the silicon, right? So that accuracy of the model is also important, right? And how do you the accurately model the cost yields, because different foundries are giving you different chips. You have to put in some model to find out what is your yield going to look like, right? Similar thing, cost as well, right? And testing. We talked quite a bit about testing is one of the bigger challenges today, right? How do you take all these 46 chiplets in one of the chip and I create a product out of it? Which chiplet is creating a problem? How do I know, right? We need to know about that, right? So maybe verify it upfront before you plug it in. At least that will reduce some of the risks as well, right? Wafer level testing is one of the example where you verify it upfront in the wafer testing itself, then you put the chip together. At least you will kind of minimize the number of issues you might see, right? So, or we need to create some kind of standards, right? When this chip is talking to this chip, we create that standard so that we understand what we're talking about, right? So with that, I think I'm open for questions and maybe all of us can take questions, right?
Any questions?
I think we're right on time, so we have 30 minutes.
Time for 10 minutes at least. 20 minutes of questions.
I have a question. We have a good time.
So I just wanted to know that you talked about the thermal crosstalk. So once your chiplet is already done and you are seeing that because of the thermal crosstalk, it is affecting the other chiplet, then what are the precautionary things you are doing? I mean, whether and the latency is also involved there. So what are the things or what are the measures you're taking while layouting, or I'll say while keeping all those chiplets together then?
Okay, so let me try to give the answer.
Yeah, this is a very good question. So there are two things, right? One, if you know while designing the chiplets, you can take some action. Think about this, the silicon itself is work as a very good heat dissipation agent. If you can keep a CPU at the center, it acts much more better than if you keep at the edges, that you know. So good to plan upfront where you want to use the chiplet. So I try to keep the CPU a little far away from the edges where you are trying to create the connectivity with these two. Because typically when you try to connect with these two, that interface is not that highly dense. Because you also need to put the IOs, and those IO and die-to-die repeaters when you try to keep it, typically it's not your hotspot. Typically, there could be a different corner switches. So ideally, when you plan the chiplet, try to keep the CPU or execution unit. Let's say if you take CPU, where you see the hotspot? You see that most of the hotspot in your floating point unit, APU unit, or if you have a extra speed of engine like an ABS or kind of a resonate 50 kind of an algorithm, where it goes to a recursive kind of a stuff, where you see the typical hotspot. Try to plan that upfront so that away from the edges, and when you are trying to put that into the repeaters, then you can actually take that upfront. That's a floor plan related activities or a chiplet placement related activity. That's a stage one. Stage two, if you have already missed that opportunity,
then what options left over to you? Left over to you, you may use some of this, the materials, what you keep it, the density of that at the board, just below that hotspot, you can sprinkle around. You may have seen some of the commercial solutions available. You may see a fine grain, little bit of blackish materials and stuff like that. So you can use those recipes kind of stuff. You can use the thermal purified. You can use the cooling agent differently. Nowadays, you are seeing even in silicon, people are putting inside the liquid nitrogen to get the performance, right? But those are your post exercise when you have the pre-stuff not there. And each of them has its own degree of freedom. You may not find out a complete solutions by one recipe. Some cases you will give you a couple of degrees and get this. So I think what Rupesh is trying to talk through, and when I was referring in the builder, you plan that upfront so that it doesn't come to you as a surprise. So that, oh, I am now going to launch the product and I am realizing I have a problem. That's a problem for you, a problem for your customer. And the solution of that also at that point of time will be not the optimal. Does it answer the question? Want to add, Devrana, Rupesh?
No, that's good.
Since you highlighted was this design aspect and how we have to plan this out upfront, right? I mean, sort of co-design in the sense when you're building a die and plan the package part of it and so on. This problem is something which is chicken and egg. For example, even existing monolithic designs, people say that we should co-design. Obviously, there's nothing new about it. People have been talking about it, but the package design, for example, lags behind the die aspect of it. People don't get the package parasitics when they want to plug in and look at groups and so on, right? How do you think this problem would get solved when you have a 3D or 2.5D? You still have the same basic issues. If you have an older die, maybe yes, because now you have something which is already done, you can integrate, but the aspect of co-design is still not completely solved because what is going to be new when you start doing 3D, which will fix this?
It's not going to fix it, right? I think what we're saying is co-design has to be left shift, right? So we have to think about co-design more.
People already know about it. Yeah. It's been there. People, for example, even right now, people build a whole SoC, and within probably a couple of months before tape out, I don't know how it's there, but most companies that I worked in, the full chip power or full chip bio drop or group analysis comes in probably like a couple of months before tape out, right? And that's not what you're saying. You want it to be co-design. Co-design means probably not too far lagging behind, right? In this case, when you have thermal issues, package, DIY issues, these things don't get resolved. How do you at Intel, how do you manage this? If you're saying that this has to be a co-design, I understand this is a good thought process, but how do you fix this problem?
So I think the first thing is it has to start from basic floor planning, right? So I think what your point is that even in the monolithic design, we also kind of consider some of these, but that is the one which you are designing, one SoC. Now you have like multiple chiplets coming across. You need to know what floor plan that particular chiplet has, right? And that may be from the off the shelf and from the different technology as well. So now the package person has to work along with that multiple chiplets, trying to understand where the pieces are. Without that complete picture, you may not be able to design the power delivery to it. You may not have thought through what are the different powers has to go to that particular chip, right? Or maybe the IOs are in different chip. What are the different IOs are there? What is their spec? So what we are trying to say is more than what it was. Some of these standards are going to help data exchange much more better way, right? Let's have a chiplet. I'm going to give you the standard of format. So you're going to plug that into your package tool so that you can see the complete picture. So that's what we're trying to say, that the work models and the standardization is going to help you in the direction. Does it help answer your question?
Partly, but I don't think this is a good, because I think people know about this. And what I'm trying to say is that this is not something which is people, the lack of, not intent, it's lack of probably the processes probably never really align. You always have this lagging behind, it's natural thing. And then therefore, when you have a 3D or 2.5D, there's going to be even more lag. Yeah. Because you pick a few dies off the shelf, you have a package which has to be continuously be reiterated. As you said, you want to move things around a bit. This whole process is going to take this, I don't know how this will get resolved.
Yeah, so it's to be planned, right? As you said, and just to add to what Rupesh has already indicated, the way to look at it, you should a planner team along with the package team need to do that tech readiness job. Maybe different company has a different name, but the tech readiness, that basically means you already have a landing zone analysis done. So if you don't enable that and you try to do it as a post exercise, which is a monolithic world, many SOCs, vendors are able to do that because you are essentially using the same socket, similar package, similar monolithic, die. You are changing the CPU speed kind of a thing. So you know by and large stuff and it fits there. When you are trying to change this kind of an ecosystem, you have to plan that concurrently. So it's not a serial run. You have to do a concurrent run. You'll make few mistakes in that process, which we call as a tech readiness. You will do a course corrections and move on. So there is no one fit answer to that. It's a work model questions. You instead of earlier, maybe you have a luxury that fine. I know I'm making a derivative chips or I'm making a chips which is a performance booster. So I have a platform. I know this. I have a package type, which also a legacy type. Now all I'm doing it, I'm changing my monolithic die, which probably earlier was 100 millimeter square, and it's putting a number to a 120 millimeter square. I'm changing the CPU speed by another 500 megahertz or 1 gigahertz kind of a stuff, an incremental booster. That kind of situations, your line of thinking is different. On the other hand, when you are trying to do a separate class of product, all he's trying to say that you need to fine tune that at the tech readiness page, whatever name in your company you call that, is basically a early phase. Before even you commit to your management, this is the performance I'm going to get. If you don't do that, essentially, you are going to be committing something to your management as an engineer, and you will be not able to meet that, or you may not be able to meet that. You have to be a little more focused. Does it answer your question?
There's usually a lot of estimation and budgeting.
Yes.
So I think that's the left shift part. I think not usually a one-way answer. Since there are metrics that you push down and then work to that target for each block, each of your high performance cores, work towards that target, keep under the target as you with the budget.
Hi, is UCI standard open to everyone?
Yes, it is.
Open to everyone. So it's a connected question. So is the industry veering towards a scenario where one chiplet will be manufactured by one entity and then its separate chiplet is manufactured by a second entity and second entity might be packaging the whole thing?
Absolutely, absolutely, you got that right. So not just one part is there are multiple flavors to it, right? You could have one company that does not have a fabless company that's coming up with the logic that's going inside one chiplet, and there's another company that's making the logic which is going inside another chiplet. Both of these companies might be using different fabs. For example, Intel has its own fabs. It might be manufacturing one of the chiplets in its own fab. It might be taking another one from TSMC, Samsung. They can all work together, all using the same protocols. For example, UCI is an example of that. Absolutely, and that is the power of disaggregation. That is why everybody's moving towards it. Let's say gives you a lot more flexibility.
So the design, the functional aspect of UCI is the physical aspects of it.
Yes, the file, whatever I shared today, right? The file, the link layer, the protocol layer, the few protocol. Yeah, it was released in May 2022, which was May last year. UCI consortium is an open consortium with a whole bunch of companies. You can just type it on Google. You should be able to get it.
So can academy actually integrate it into their design process?
I think so. Yeah. Yes, it's an absolutely
It's
open.
open standard.
Open standard. Intel donated the first specification, but it's now a consortium of a huge number of companies that are taking it forward.
That's the intent. So what you need to do it actually, you can download the latest protocol. You see what portion, what we use it. It doesn't need a license. You can just use it.
And whoever is your vendor, if it is something ready-made solution, somebody is already giving it to you, and being you are trying to use for academic purpose. So I don't think you should be having any problem because nobody is charging anything from that. And even if there's somebody is charging, probably they will give you a very discounted price.
Yes.
Yeah, so my question is regarding this, that we talked about the chiplets being stacked. So do we have, which I asked you in the break also, do we have a case where we have one chiplet being manufactured in or being designed in FinFET, and the other one is in the bulk technology of planar, or I would say SOI technology? If is there any case like that which is already being done? And if that is being done, what are the challenges being faced while doing while stacking any FDSOI technology or a FinFET technology together?
Yeah, I think this is a good question. We have not done that, at least. But theoretically, you can, using a silicon interposer kind of a techniques. If you are trying to do a kind of a rapid prototyping and stuff, I'm not sure whether you will find an optimal solutions there or not in terms of the speed and power and performance. But using the silicon interposers, you may explore to do that. As I said, we have not done this for a product yet. We think three of us. There could be, if there is a big company, they may have done it some other places which you don't know. So I will not be able to give you a definite answer, but theoretically, using a silicon interposer as a technique, you should be able to do that. And you need to negotiate with your, packaging partner in terms of adjusting the height and the glue and the organic materials. So it's a little unknown territory. Having said that, there is a path to go there. Technically, you have to do the tech readiness job. Did I answer your question?
You touched upon the sort of yield. I assume, you say yield, I assume you're saying that you don't have unique dice, and it's not based on known good dice. Say yield,
So what I mean by that is when you're trying to have these chiplets from different process nodes, they might yield different way, right? So when you're trying to create the yield analysis model based on the, you need to plug in all these different chiplets yield analysis models together.
different way, what do you mean? You're unsure about a specific chiplet, not yet.
In the sense that if you have a chiplet and you have a different components in the chiplet, and based on the component, let's say you have too much memory, maybe it deals different way compared to when you have a CPU, right? So it depends on that content. And hello, was there a question? Okay. So you have to do early prediction of the yield in the early process, right? You need to know what is your real yield going to look like, right? Analysis, basically.
Doesn't that blow up your DFT because you're saying that you're unsure about what is and test parts and methodology. I used to have, we have the saying, you have specific product, you have said you have 47 chiplets. The number of combinations and test patterns that you have to get. Only the industry, the way I understand it, is that it's pretty sure that this guy is yielding any sort of
No, that is still the case, right? That is after the manufacturing, right? As I was saying, right, you have wafer level testing. You do a testing, right? And you know that that die is good, known good die, and you put it in the package, right? You put it in the package, then you might still get better. I mean, it's not that it's 100% perfect because you might have assembly losses, you might have the package losses and all that stuff still adding.
Defects per million.
Yeah. Exactly. So
if you sort of take all of them together, obviously the yield is come down, but each yield, I don't know how you That's a question. So is it based on known good die or not based on known?
No, it is known good dies. That is one portion of it. That's after the fact, right? After manufacturing, you're trying to get the known good die and put it into package and trying to get a product out of it. But even before you do any of these manufacturing, you have to do some kind of yield projections, right? On, okay, based on this process node, based on the good dies per wafer, or based on the components of the nature of the die and process of the die, you do some kind of estimates. That is the estimate which I was talking about, yield projections at the beginning.
And then in terms of so you're building the dies as you should, right? The design process to follow for a given die, or anything, going to be for a chiplet in any case, right? So how does your design margin and maybe sort of assign variability design margin, which sort of has this aspect of this environment settings in a which is different than a big die? How does it change your design space performance? Because let's say if I have isolated die and I have a certain expectation of, as we do in monolithic, you have certain performance optimization point, and that could be optimal. You take it in isolation, but now the space sort of blows up for you, and it could be used in different products. How do you then decide on what's the right optimization point to set for a given, let's say, an accelerator which has so many instances? And is that something which you guys explore in your this physics model or optimization model?
Yeah, so you want to answer.
So you're talking about the VF curve optimization?
Not the VF curve, but in general, let's say, for example, if you have a synthesis spec, right, or a physical design spec, or any sort of design spec, if you have monolithic die, you have a certain voltage frequent performance power optimization point, right?
Yeah.
More BTs, more sort of area, sizing, whatever, right? You have different BTs. So when you have an isolated monolithic die versus when you're sitting in a 3D or a 2.5D, the space is sort of different for you. And obviously you have another dimension of being used in different products. How do you then decide, how do you set the settings for margins, the right corners to pick, and so on and so forth?
So I think that's also true for even monolithic dies where we have a range. I mean, maybe earlier we would have a fixed design point where we'll optimize the, the bandwidth, the performance, as well as the, the VT curve basically. But now even in monolithic dies, we will have ranges of
multiple corners.
Yes, yes. And then depending on the product solution that you're picking out, I mean, obviously your dialect needs to support a range. Let's say the product planner has to look at all of these different dialects that are working and then set them together to see what works for that particular solution, right? Obviously, you will not have infinite combinations. For the product planner has to make the decision based on the different dialects ranges, what works and what doesn't work. In general, the dialects are now having, like you're saying, let's say bigger ranges than what we would have probably seen in a monolithic die. So we are planning for that, a much higher frequency range than, and again, all of those power saving mechanisms and all have to be thought through, because let's say you have a dialect which you are not, pushing to the highest limit in a particular product, you want to be able to run it at a much lower power budget as well as a much lower performance budget. So that ranges are there. Now you have to decide on your product what works best for those combinations.
So what I'm asking is, does it mean that you fix, let's say you give up on area in the sense you try to design for the best possible performance or power, you get a baseline area spec? Because people obviously try to be aggressive and you have all these 3 PPAs and so on.
Yes, correct.
So, but you sort of fix the area curve cannot be optimized because you have so many dimensions to explore. But you add and try to recover other aspects and other parameters by adding more configurability and operability.
So again, each of those dialects, for example, probably the core dialect, I'm only concerned about my performance, max frequency that it can get to. But maybe on the IO dialect or on the main dialect, I'll look at, okay, maybe this doesn't need to go to the highest 4 gig or 5 gig. I probably can work with 2 gig or something like that. Then I'll think about optimizing the area or the other, things of the PPA that are more important for me. And again, power has to always be there in the background, right? Depending on what is the performance that I'm running my dialect on, I should be able to tune my power consumption of that dialect. And so, think about all kinds of different low power modes, not just the turning of the power, but maybe reducing the frequency, dynamic voltage frequency scaling, all of these things, which basically increases the range of operation of your solution.
You take one more question and we'll close. So what is the
For IoT kind of,
one second.
for IoT kind of solutions, energy is one of the main constraints.
Exactly.
So as the sir has mentioned that power is also need to be transmitted, and as well as delay is also introduced. So what due to this technology, what is the effect of energy like PDP and EDP kind of energy metrics due to this technology? I'm just is there any analysis for the same or not?
Yes, so if you look at the IoT design, right? IoT design, typically you have a different challenge, and IoT is a very fast term, by the way. When you mean by IoT with a handheld device.
Specifically, I'm talking about edge computing. Then
edge computing, if you look at it, right, that is at the device's premises where the power supply is plugged in. Right? So if you look at the edge computing device, you are basically limited by a TDP budget, saying that I'm making a 50 watt or a 100 watt or a 200 watt kind of a power consumption. And now, what is your performance you have to get at the edge? Whether your main stock is a CPU or a GPU for the kind of edge applications what you are running, you give the maximum power to that. To answer to your question, also similar line, when you are trying to plan it, you give the highest power or a credit to the CPU or a GPU or accelerator what you are trying to design. And typically, you keep a separate voltage rail so that you can fine tune that. There's no point that for the CPU to get the highest TDP, you may increase the voltage, let's say 1.2 volt. But you have an IO with just bunch of level shifter and enable planning, you can run at even 0.6 volt. If you merge them together, you have a challenge. So the best way is to define the power state, give the highest credit to the CPU or the GPU, or if you have a specific AI application running on that, give to that, and plan accordingly. So your power state need to be much more fine-tuned when you are trying for an IoT if it is an extremely TDP constrained conditions. Right? So you define every in this process, your number of power state is going to be increasing based on the design what you are choosing. Maybe instead of typically if you have 4 power state, you are increasing to maybe 7 or 8 or a 10 power state. And managing those sequence, you have to do some electrical modeling and functional validation so the protocol doesn't get disturbed to that. There's an extra work for you. So best is to do the power state consolidations and focusing on the core performance what you need. And the remaining portion, you just run what is the minimum clock need to be tuned to. Don't unnecessarily extra clocking to burst the power, which you can give essentially to your CPU, GPU, or a accelerator, whatever you have. That's the best way to go forward.
We'll take one last question and.
So you had already mentioned the defect projection for different components. So can you give the ratio of compute versus memory defect for our technology?
Yeah, I think those I think depends. I'm sorry?
Can you give us a ballpark number?
It depends on the technology, right? So yeah, I don't have any numbers on top of my head, but do you have anything? Defect?
Yeah, I think unfortunately you will not be able to share that data. It depends. See, let's say if memories are already triple tested already. Let's say today if you take it 45 nanometer memories as an example, you will see that it is extremely high. Right? If you take today 5 nanometer or a 3 nanometer experimental memories, you will be seeing there is a lot of issues. So why I'm not going to this number is because there are a lot of manufacturers are involved there. Here itself, maybe there will be a 5 companies representing that. It's not fair for me to comment on any absolute number. When initially it comes, why it is basically very sensitive. When initially it comes, the design houses see even a single digit number there, and then they gradually go to the higher level. With such a wide range, I don't want to misguide you on that.
The reason I was asking was you had talked about co-designing.
Yeah.
So if we know the weightage about the failure, right, then we can accordingly give the weightage and not the rough starting point.
Yeah, but over a period of time, wherever you're manufacturing, they will solve your problem. So basically, this is the initial kickoff phase you have to go through. Whatever the vendor you are choosing, they will essentially solve your those problems, which are not induced by you at the beginning. By design, if you are making some mistake, then the fab house cannot help you. Otherwise, those problems will essentially be solved by them. Maybe there are some pattern changes they will do. a little bit systematic failure, they're not able to do it. Maybe some lining in some areas or somewhere there is a problem, they will cause it. So they will give you the solution at the end of the day, and the numbers quite radically varies.
Thank you. Thank you, everybody. Thanks for being a wonderful audience. Thanks to speakers for a very engaging session, taking us through packaging technologies, CAD, floor planning, and talk about it. I mean, multiple technologies that have to come together to get to where you want to be. Very interesting session and very good set of questions. I will we answered you. With that, I'll hand over the mementos.
Yeah, we thank you, come to, and thank you, thank you. Let's put it so that-
Thank you.